Can you hear better? Yeah. Okay, then I want to remind everybody with the code of conduct, we are a little bit over midweek, then it's good to remember. And I add a link under here how to report any ethical concern that you have with anything happening. And you can do this anonymously. Then, alas, Meet a Scientist session. This is the group of people and the room. I updated all the link. Yeah, this is the people that didn't sign up are signed up now. Also today, this is where can you find the documentation. Then this is where you can find the documentation. You know this now. And we will have we will split in room. We will assign room, not room, area in the library and the diamond room today. But again, you are welcome to switch between group. And again, it's a self-paced lab. If you feel that you want to work on the previous section, you still can. Another logistic. Today, we will have no coffee at the interruption, the first interruption, but we will go to take a picture. We were going to go outside, but it's raining. We will see. Otherwise, we will go in the stair we have as an ID. But just after this, we will go take the group picture. And the last thing, it's about the people leaving tomorrow. Yeah.
Great, thank you. So we talked a little bit about this for anyone who was here yesterday afternoon. So if you're leaving, your flight is on Friday, come over during one of the breaks and check with us. I've got a sheet. I just need to get an idea of how many people will need to be on the shuttle at what time that will take you down. We say just down the hill. You might be familiar with this, where the RTD station is, and then there's a bus that goes directly to the airport from there. So the important thing, too, is make sure you check out on Friday if you're flying out on Friday, and to bring your bags with you. We'll have a secure area over here. There'll be one of us here to keep an eye on them the whole time. There's just some hints I was thinking about last night. If you're leaving on Saturday, let us know. Sometimes because we're ending early on Friday, people like to go somewhere around town. But if you are planning to go right back to the hotel, if you could let me know by noon today, I'm just trying to maybe make some shuttle adjustments for the bus on Friday that will go back to the hotels on Friday. So let me know that. Just some considerations. I know that you've all been using GroupMe, but you can think about coordinating your rides back to the RTD. The bus is definitely the fastest and cheapest way. But of course, if you're traveling at a weird time, we gave you those links for 8 Black and some other resources for getting back to the airport. And make sure you check the RTD times, because the bus does run different times on weekends. And as I said before, it's move-in weekend, so there'll be more traffic in Boulder on Saturday. And I found this really cool website that you might want to bookmark if you're ever coming to Denver again, is that you can check the security wait times right on that website. So you can take a look at that, and as soon as your session here starts, I'm going to post these slides so you'll have access to that. But thank you. If you have any questions, because we're streaming and recording, just come ask me in the lobby. I'll be here all day.
And we can add a link to the RTD.
Yep.
Yeah, to the RTD schedule here. And be careful, they have what they call eastbound. It's the one that goes towards the airport, and westbound, it's the one that comes this way. But they assume you know what is east and west. And okay. Okay, then if there is no question, we are going to move to our first speaker of the day, Rebecca. Okay, then she's going to talk about the atmospheric chemistry in the model.
Great. Is this on? Got this on? Great. So let me just start my timer so I know how much time I'm having here. So my name is Rebecca Buchholz. I'm one of the liaisons for the Chemistry Climate Working Group, and Simone Tilms is a co-chair, Rafael Fernandez is also the external co-chair, Francis Vitt is our software engineers, and Sean Honemichael is the other liaison. So this morning, I'm going to talk to you about chemistry, atmospheric chemistry, and aerosols. And I love talking about chemistry, so this is going to be fun for me. But just letting you know, there's going to be a lot of information. Atmospheric chemistry is complicated, and there's going to be a lot of information coming at you. Think of this as the first point of information, and if you want to know more, come back to these slides, read them again, access the documentation that I reference if you want to go deeper. Yeah, so let's get into it. This slide, this image on the left here, on the right here, I like because it shows how complex this chemistry can be. We have all these different types of sources. We have transport of chemistry into the upper atmosphere. You can have impacts of this chemistry locally, and it can also be transported up and have impacts in the upper atmosphere. This stratospheric-tropospheric exchange can happen. And you can also have transport downwind, and impacts from emissions or chemistry that can happen in one place can actually impact far downwind, like we see with the fires from Canada impacting here, for example. And so this is an outline of what we're going to be talking about today. I'll have a couple of slides of why we care about atmospheric chemistry. Then I'll go into really how we start to define it in the community Earth system model. If I have time, we'll talk about a couple of applications, some experiments that we've run with the model, and then leave you with a slide of where to get more support and information. So why is atmospheric chemistry important? One aspect is it impacts our health. The atmosphere is where we live, and there's a lot of chemical pollution that can impact our health. The two main chemical constituents that we are concerned about that impact our health are ozone pollution and particulate matter. So ozone pollution, ozone in the stratosphere protects us from UV radiation, but down here at the surface, it's actually harmful to human health. It causes inflammation and worsening of symptoms for people that may have asthma, like me. And ozone isn't actually emitted into the atmosphere. It's created from all of these precursor gases. So in order to understand how to control ozone, we actually need to understand how to control all their precursors and how they go into creating this ozone. And so modeling can really help us in understanding that kind of a situation. The other aspect is particulate matter, particularly this PM2.5, which is particulates or aerosols that are lofted in the atmosphere and stay lofted, that are less than 2.5 microns. They can get deep into the lungs and cause cardiovascular impacts due to impacting the cardiovascular system. And so there are lots of different sources of these trace gases and aerosols, particulates. And what we're starting to find, particularly for the particulates, is that different sources may have different health impacts. So for example, fires could have different impacts to traffic particulates. So it's a really growing area of research and important for atmospheric chemistry. The other aspect is how atmospheric chemistry interacts with climate. So these are two diagrams from the recent IPCC report showing the impact on the right there of changing global surface temperature due to different components in the atmosphere. CO2 at the top there has the most impact, but there are all these other trace gases and aerosols that have impacts as well. There's CFCs and ozone and methane, water vapor and aerosols as well. And they all have differing impacts on temperature responses in the atmosphere. And so modeling these correctly is really important if we want to understand what's happening in future. And then finally, the final kind of motivation slide is this stratospheric ozone. We know that it protects us from UV radiation, but really understanding what the ozone hole recovery is going to look like, how CFCs are going to change, and if there might be a slowing in the trend of that ozone, if the CFCs aren't going down fast enough, where is that coming from? There was a recent study that actually used modeling to target and understand where that slowing trend was coming from. So there's the motivation of, some motivation of why we're interested in atmospheric chemistry. And now thinking about how we add it into models. Really, if you think of the CESM model, it's this model that has a lot of different grid boxes, right? So it's just this latitude, longitude, altitude grid boxes. And if we think about one grid box and what's happening for a chemical in that grid box, the amount of chemical there is dependent on the sources that come in and the sinks that go out. And we're going to step through all of these processes that impact the chemistry for this particular chemical, Chi. The first thing we'll talk about is emissions. So emissions in CESM, there are 4 different ways to define emissions. Oh, I'm sorry, that resolution didn't really come out great in the bottom left. But so there's 4 different ways of defining emissions in CESM. We have files that are read in that are surface emissions. So these are latitude, longitude, time files that have emissions of things like anthropogenic, biogenic, fire, ocean, and soil emissions. The other option is to have vertical emissions, and so these are similar files, but they now have an altitude range as well that include aircraft, volcanoes, power plants. And if you want to use fire as a vertical option, you can also do this with the vertical emissions, making sure not to double count and put them in surface as well. The other emission type we have is interactive. So this is where the emissions actually come from other components in the model. So the community land model, for example, will tell us some things about biogenic emissions, how much vegetation is going to emit based on its stress level or something like that. And then the final way of defining these concentrations or emissions is these lower boundary conditions for things that have longer lifetimes, like CO2 and methane, etc., and that are needed for these longer time periods. We add those in as more of lower boundary conditions rather than emissions, because they can have these long-term trends. And in the bottom right here is some examples of those lower boundary conditions. So those are the 4 ways that we look at emissions. Here is an example of how we define the interactive dust emissions. On the left at the top is what is the current default, and on the right is what we're moving towards. So dust is based on horizontal wind fraction and soil moisture right now that comes from the model. But in the future, there's also going to be drag partition and another couple of wind impacts. And the 2 images on the right look much closer than this left image and the far right image, which is the observations. So we're going towards a better representation of dust in the model. The interactive emissions for biogenic emissions is called Megan version 2.1, and this is based off leaf area index and emission factors and soil moisture, and that's what drives the emissions from biogenic sources in the model. Okay, so that's the impact of emissions. Now let's talk about chemical production and chemical loss, and this is for both gas phase chemistry and aerosol processes. So this gets really complicated. We have over here in the diagram is an example of the kinds of reactions that we have. And then a list on the right there is the kinds of reactions that we have to think about: photochemistry, gas phase chemistry, heterogeneous chemistry, aqueous phase chemistry, and gas to aerosol exchange. And in this diagram, there's a lot of NMVOCs, so non-methane VOCs. That's not just one species, that's a lot of different species. So you could imagine that this diagram is actually really complicated and tries to simplify down for a group of chemicals. This is tropospheric chemistry. It's quite complicated. And then we also have stratospheric chemistry, which is different to what happens in the troposphere. So we have ozone destruction and halogen chemistry, and that's really what's driving this ozone hole that we see here in the observations. And so thinking about how complicated this tropospheric and stratospheric chemistry can be, we have to make choices between the complexity of our chemistry and the expensiveness of the model. And so that's where we come up with a whole bunch of different chemical mechanisms that you can use depending on what experiment you want to run. So on the right here are the different types of chemical mechanisms that we have. The default that we use when we run a chemical, a CAM-CAM, a CESM with chemistry simulation is this TS1. So it's tropospheric chemistry with the T1 mechanism of the tropospheric chemistry with stratospheric chemistry as well. And then we have this diagram over here on the left shows you the different complexity. So we can see from the left there are more compounds, and so there's about over 200 compounds and over 500 reactions. And this is happening in each box of the model. So it starts to get pretty expensive fast when you have every box having 200 extra chemicals and 500 reactions happening. Not to mention all the wet deposition, etc., that we'll get to in a minute. So this TSMLT is something that's used in Wacom that Mijong's going to talk about later. So this is something when we're looking at even a higher top of the model, but the CAM-CAM top usually uses TS1. We also have this T4S, which is comprehensive stratospheric chemistry, and T4 tropospheric chemistry, which is a simplified version of the tropospheric chemistry if you want to run longer time periods. And then we have this specified oxidants with greenhouse gases if we want to run like climate simulation length, 100-year kind of simulations. Okay. So the other thing I wanted to talk about is even if you're not using the chemical version, the atmospheric chemistry version of the model, there still needs to be chemistry in there because we have those interactions with the radiative balance, interactions with clouds. We need to have chemistry in there to actually have a correct representation of what's going on. So if you're running just CAM instead of CAM-CHEM, you still have chemistry in there, and the way we do that is we run a full chemistry version of the model, save out all the important species, the oxidants, and then we put those into the CAM version of the model. So there's no interaction with the chemistry in this CAM run, but there are these lists down here of prescribed ozone is used for radiative calculations. So this ozone that's read in from this other version of the model is used for radiative calculations in just a CAM version of the model. And so there are other points here as well. Okay, so that's chemistry. We also have these aerosols, a little bit more detail on the aerosols. The way that these particles or aerosols are defined in CESM is using, in the default mode, is using this modal aerosol model, and it's version 4 that is currently the default version. So what happens here is the aerosols are lumped into these different modes. We have this icon accumulation course mode. The numbering of those modes is historical. The middle one is A1, and then we have the icon is A2 and the course is A3. And then we added this fourth mode as well, this primary carbon. So we have primary emissions of organic carbon and black carbon as well. So those are other aerosols that are emitted. The other kind of aerosol that we have in the model is secondary organic aerosol, and I don't want to spend too much time on this slide. The main thing on this slide is that in the simplified chemistry for just running CAM, we have secondary organic aerosol read in from a file. And then for comprehensive chemistry, it is more complicated. It's a more physical approach where it's using the volatility bin sets, and there are 5 volatility bin sets, and it's based on the volatile organic compounds that are read into the model and processed through the chemistry, and so they're converted into the secondary organic aerosol. Okay, so that's the chemistry and aerosol, chemical production and chemical loss. The next thing I wanted to talk about is the advection and diffusion. So this is actually coming from the model. This is coming from the atmospheric component of CESM. And here in the diagram, it's denoted as inflow versus outflow. What I wanted to talk about really quickly was this free running versus nudged versions of running the model. I'm not sure if you've heard about that yet. Free running is where you rely on the physics of CESM to drive all the dynamics and the vertical lifting, etc. When you nudge a model, you're nudging the meteorology towards reanalysis, and reanalysis is really close to what actually happened in reality. So if you want the wind fields, etc., to be really close to reality, you'd use this nudged version of the model, and that would then define this inflow and outflow, or this advection and diffusion, be impacting the advection and diffusion of your chemicals. And then the next thing I wanted to talk about, and the final thing, is this deposition. So we have wet deposition and dry deposition in the model. And these have definitions that we have added into CESM. The wet deposition is a first-order loss process. It's based on solubility factors of aerosols and chemicals, and includes in-cloud and below-cloud scavenging rates. I wanted to shout out to Denny Murray, who's currently an ASP graduate visitor, evaluating the wet deposition against observations in the top there, and it's actually looking pretty good. The other thing I wanted to mention regarding wet deposition is this aerosol cloud interactions. So we need aerosols in the model to impact things like cloud condensation nuclei and ice nucleation. And so all of your clouds and precipitation depend on whether you have aerosols in the model and how much aerosols there are. So this diagram comes from a paper by Wang et al. In 2020. They described this regarding E3SM, which is a very similar model to CESM. But if you want to know more about all of the aerosol cloud interactions and what needs to be considered, this is a really good paper to go to. Okay, and then finally, dry deposition. Dry deposition in the model is a resistance model. It's based on vegetation and surface dryness. And it really, the information comes from the community land model. And there's also an impact of roughness of the surface as well there. So those are all of the impacts that we have to think of for a chemical in one box of the model, but thinking about how that impacts a global model like CESM. And in red there again, it can get very expensive very fast. So just considering what kind of experiment you want to run with chemistry can help you understand and choose which chemical mechanism you want to use. Okay, I'm going good for time here. So let's talk about a couple of applications. The first application I want to talk about is the regional refinement capability that we have in CAM and WACM. So Musica is multi-scale infrastructure for chemistry and aerosols. And what it is this ability to regional refine, so have a really fine resolution over a region of interest. So here we're looking at 14-kilometer resolution over CONUS, and then a coarser resolution everywhere else. So everywhere else is 100 kilometers resolution in this simulation here. And what this allows us is to look at exposure relevant scales over this regional refined region, but also include the impacts from transported pollution in the same model, with the same physics, with the same setup. So we're not using boundary conditions from a different model and potentially getting inconsistencies there. So this is a really good way to look at air quality. You'd want to use like a lot of chemical reactions in this chemistry. So really looking at case studies of air quality with this kind of a model is what I'd say is mainly used for. You can just look at CONUS, but we have a lot of different regions that are available. We also have South America and the Arctic and regions over Southeast Asia and Africa. And you can also create your own region. So it's you can create your own user-defined region. And the impacts are, we can see differences over in those little movies, we can see differences over the regional refined area, but we can also see differences in the outflow. So the resolution of that regional refined area impacts the outflow as well. And the other application I wanted to talk about was this impact of chemistry on climate. So the Australian fires, the huge extreme Australian fire season happened in 2019-2020, where basically all of East Australia was on fire. And what we did in the model with John Fasillo, we added in those Australian fires and compared the aerosols from those to what would happen normally in what was going to happen in the climate. And we found that the Australian fires potentially created a deeper La Nina than what was going to happen originally. And so we were able to do this because we had this chemistry in the model. And so we can see impacts here on the left of the albedo being impacted by those smoke particles, and then cooling in the sea surface temperature, and the impact on El Nino in the red line in the far right. Okay, that's all I wanted to say today about chemistry. If you want some more information, we have a wiki page for chemistry, so that's both CAM-CHEM and WACCHM. And there's this CAM documentation that I really encourage you to look at to get more information, deeper information about processes of the model. There's a user and scientific guide. We also have a regional refinement wiki to talk more about those regional refinement options. And then there's a forum where you can ask questions or search for if your question might have already been asked or answered. And then our contact details are on the right there. So I think now we have plenty of time for questions, and thanks for your attention.
Thank you so much. Then a question. Yeah.
Thank you, Rebecca. Thank you for the nice talk. And I have a quick question about the emissions in CESM. Could you come back to this slide?
The slide of...
the very early, the slide about the emissions in CESM, emissions of aerosols and the low boundary conditions.
This one?
Yes.
Yeah.
So I'm curious about, would it be possible to set the emissions of greenhouse gases rather than its concentrations to run the model? Because sometimes we found that there is changes in emissions in greenhouse gases rather than the concentrations. So I'm curious about this.
Yeah, that's a really good question. I know that we're working on methane emissions and methane emission version of chemistry right now. I would say it can be difficult because, particularly for CO2, it has such a large concentration, like kind of background concentration, that these small emissions on top of that large background can be hard to get right. CO2 modeling can be difficult, but it can be done. But we find that for like these longer time series, and when we're looking at, say, air quality impacts, something like the VOCs and those shorter lived species can be more important for those air quality impacts.
Okay, thank you.
Hi, thank you for the talk. So I'm curious about two questions about ozone.
Mm-hmm.
First of all, how have you compared the ozone, the surface ozone, to surface station values from the EPA across the US or in China? So I'm curious how those compare. And secondly, for future scenarios, what does your ozone look like? Because that's not going to be future scenarios would specify emissions, but since ozone is not a direct emission, I'm curious what the future ozone looks like for different scenarios and how that might compare to what other models are seeing.
Yeah, those are really good questions. I'll answer the first one. So the first question is, have we compared ozone against surface measurements, for example? Yes. Ozone is something we really want to try and get right in the model. So we're comparing it all the time. We compare it to satellite observations of ozone, tropospheric and stratospheric ozone. There are TollNet ground-based vertical stations. We have FTIR stations that look at vertical versions of the model. We have field campaigns that measure ozone, and we have those surface stations as well. What we find is over the US, the ozone tends to be a little high. So the chemistry seems to be maybe a little hot in terms of creating a little bit too much ozone. I'm not sure about other parts of the world from memory, but I'm sure it's been compared in other parts as well. But that's definitely something, it's one of the first things we look at when we make any chemical changes in the model. How did it affect ozone? And is that better or worse compared to the observations? Yeah. So that's what I'd say about comparing with observations. In terms of future, I don't know. I don't know anything about the future simulations. I'm not sure if somebody else in the room would know about ozone in future simulations. But what I would say is what you could do is you could have different versions of the future model and run full chemistry in those future versions and then see how ozone would change. And I'm not sure if that's been done with CESM in its current form.
Right. I am really curious if that's been done or if those data
Yeah.
sets are out there.
Yeah, I think something that's super important for future is fires, and interactive fires is not currently really used in any Earth system model. And so, how is that going to impact the future?
And I'm interested in how it affects vegetation
Yeah,
using the
all of
ozone for that.
feedback. Yeah.
Thanks for a great talk. I have just question about the notching things. So there's a
Yep.
free running and a notching, right? And it seems that notching strength is a homogeneous for the entire atmosphere. So can you apply certain regions as notching differently? For example, like vertical variable notching, so notching's less in the surface and the notching hard in the top of the atmosphere.
Yes, I believe that is now available in the new version of the nudging code, that you can nudge stronger closer to the surface and nudge weaker at the top. It might be something that you'd have to look into the source code for more than a comp set or a name list variable. What is available also is nudging with the regional refined. You can nudge outside the region but not inside the region. So you could have free running inside, say, the CONUS region, and then outside the region, nudge to the reality of the reanalysis.
So new version is the Chem7 then?
No, in CSM2, we had an older version of nudging a couple of years ago when we updated that. And so, yeah,
Thank
the
you.
nudging right now should be able to do variable impacts. Mhm.
We have time for a very quick one. Yeah. Do my size.
Thank you for the talk. I'm just curious, I'm assuming you've run versions with the prescribed chemistry versus the dynamic chemistry. What are the major differences within the climate system beyond just like concentrations of the various species?
The difference between, so you're asking the difference between like the CAM version of the model and the full chemistry, is that what you're asking?
Yeah, like the dynamic versus the prescribed chemistry versions.
Okay. We're aiming for it to be really similar, right? So that's part of the reason why we run the full chemistry version of the model and then take those fields and put them into the CAM. So the chemistry that you're going to be seeing is going to be similar, but you're not going to have those interactions with the chemistry. So for example, if you're running these long climate simulations and you have 100 years and you might not have the interactive fires impacting the chemistry as much, that can have impacts on precipitation, on winds, so you will see potentially differences in other fields than just the chemistry. But it's this balance again between the complicated and the expense of it, and the difference is small enough on those uncertainties on those climate scales. Yeah, is what we believe.
Okay, thank you.
Thanks.
We are going to go outside to do the picture, but Rebecca will be there after, and she will be all day here in the lab session also. Then you can ask more questions. Then usually you have private time with the speaker to ask your private question about if you don't want to ask in front of everybody, but she will be there.
I'll stick around.
Okay, thank you so much. coming back. Now we have the next talk. What do you say? What you want everybody quiet? No, he gave me a trick when he want everybody go quiet. And yeah, but he doesn't want to share. Okay, sorry. Sorry to put you on the spot. Then Mijan is going to talk about WACAM. That's another version of the atmospheric model.
Thank you, Cecile. Can you hear me okay? Yeah. So today, I'll be talking about WACAM, the high-top configuration of CESM. Hi, everyone. I'm Mi Zhang, and I'm at ACOM. Today, I'll be using some of the slides from last year's tutorial that Nick Davis created. And my goal for the day is to introduce WACAM and all the cool science you can do with it. So after 20 minutes or so, you feel like, oh, I'm gonna be WACAM user, and welcome to the community. So we are whole atmosphere working group. From the left side, June, myself, Rolando, Doug, Chuck, and Anne, Francis, and Nick Paratella at HAO here at NCAR, and Daniele Visioni at Cornell University. They are the co-chairs. So we're talking about whole atmosphere model. Then let's look at the whole atmosphere vertically. Let's begin from the surface. Near the surface, altitude increase, there's troposphere. And then about 10 to 16 kilometers, depending on latitude, there's stratosphere up to about 50 kilometers. And above that, there's mesosphere, and thermosphere, and exosphere. And you've learned about CAM. So CAM only goes up to 42 kilometers, and WACAM goes up to 140 kilometers. That's pretty high. And WACAM X even higher, up to 500 or 700 kilometers. So all these different layers of atmosphere has different phenomena we're interested in. For example, in the troposphere, we have weather, and air pollution is our concern. And you go into stratosphere, there's ozone layer, and we can launch weather balloon and measure atmosphere. And if you go higher, the air is getting thinner and thinner. And you can imagine progressively higher model require more comprehensive or complicated physics. That's a problem. And what physics do we need to resolve the atmosphere up to 140 kilometers? And do we even need it? Why does this part of the atmosphere even matter? So this is another simplified figure of the atmosphere vertical structure. So if you look at the figure on the left, it's a CESM. So there's WACAM, there's WACAM X. They're all atmosphere component of CESM. And we have land, ocean, and sea ice. So it has different height of model lid. So vertical structure, what's important is the temperature changes if you go high up in altitude. Troposphere, stratosphere, mesosphere, thermosphere, exosphere, as you can see from this diagram. And one other thing, there is ions. So we need to figure out different ion chemistry in the model in CAM, WACAM, and WACAM X as well. Now we just talked about vertical structure. How about horizontal scale or time scale? Let's look into it a little bit. So the figure on the left is just that. It's a figure from Mary Barth she used a couple of years ago, and I asked, hey, can I use it? She said yes. So I was so happy about that. So x-axis is time, temporal scale, from second to days, weeks, and centuries, and so on. And y-axis is scale, local scale, regional scale, global scale. So if you go on the bottom left, there is atmospheric turbulence and convection. If you're interested in those phenomena, you have to use the right model. Maybe WRF. WRF might be right for you. But if you move away from this area to the right-hand side on the x-axis, to the top on the y-axis, you see all these global feature, climate, El Nino, and CO2 variations. That's where you can use CAM, WACOM, and WACOM-X. So the whole atmosphere community model, WACOM, is okay. Looks like you can do something with it. But the more important thing is the middle atmosphere, which is stratosphere, mesosphere, it couples the lower atmosphere surface to even higher in space with different temporal scale from microsecond to longer time scale. And there's chemistry involved, and there's aerosol and dynamics as well, circulation and radiation. So it's really important to have a model like WACOM to actually simulate this coupling between the atmosphere and the right scale, right time scale, right spatial scale. Now, I'm sure you've seen something like this already. I don't know how many times. Maybe you're already sick of it. So we're looking into CESM. So CESM has different components. There's land, there is ocean, land ice, sea ice, and atmosphere. And they all couple through something called coupler. So just like CAM, WACOM and WACOM-X fit into this atmosphere component of CESM. Then what kind of forcings do we have? We have greenhouse gases, and there is aerosol, volcanic eruption, and solar variability, such as. So I'm just giving you just a couple examples. And one of the very important factor going into WACOM is gravity wave. So gravity wave is everywhere. We can't really see it with your eyes. And gravity waves have a wide range of spatial scales. And most of them are smaller than the grid scale of a climate model. Then what do? We cannot ignore it. We cannot resolve it. So we parameterize it. So there are 3 primary gravity wave sources in the atmosphere we care about. First one is orographic gravity waves. The second one is frontally generated gravity waves. And the third is convectively generated gravity waves. And those are all important to different atmospheric phenomena. For example, in the model, orographic gravity waves are important and affecting the stratospheric polar vortex, okay? And frontal gravity waves is important polar vortex and mesopause. And convective gravity waves are important, such as QBO, quasi-biennial oscillation in the stratosphere, and also mesopause. Since it is parameterized, it comes with large uncertainty. Now, let's compare WACOM and CAM. You know at least one. What's the biggest difference? Model lid is different. WACOM goes up to higher altitude than CAM. Is that all? No, that's not true. I listed a few here. Let's read through what's the difference between CAM and WACOM and why do we want to use WACOM instead of CAM. First of all, extension from surface to 140 kilometers for WACOM, and we have 70 or 110, and we're working on actually 135 level for the new version of the model, and detailed neutral chemistry models. So Rebecca touched on a lot of chemistry, but some chemistry goes into WACOM. There's something called MA, it's middle atmosphere chemistry, and it includes catalytic cycles affecting ozone, heterogeneous chemistry, polar stratospheric clouds, and aerosols, and so on. And there's another version, it's called TSMLT. TSMLT stands for troposphere, stratosphere, mesosphere, and lower thermosphere chemistry. And if you use this, you can also see the organics in chemistry in troposphere and air quality. And there are other things in WACOM There are prognostic stratospheric aerosol derived from sulfur emissions. And there is model of ion chemistry I mentioned a little bit in the beginning. The EUV, non-LTE, long wave radiation parameterization, I don't know much about, and gravity wave, drag deposition from vertically propagating gravity waves generated by orography, fronts, and convection. And we can look at interactive QBO, quasi-biennial oscillation, derived from gravity and resolved wave forcing. There's molecular diffusion and constituent separation, and there's Wacom X. What is Wacom X? Let's look at a little bit briefly here. So Wacom X is called, actually the name was much longer than I thought. Whole atmosphere community climate model with thermosphere and ionosphere extension. So it's really clever way they just put just X. I appreciate that. So Wacom X is a model of the entire atmosphere that extends into the thermosphere to 500 to 700 kilometers and includes ionosphere. Because the thermosphere ionosphere system responds to variability from the Earth's lower atmosphere, it also includes waves and tides and tropospheric weather, even middle atmosphere events, seasonal variations, and anthropogenic trace gases. And this is this nice figure that I found on their website. If you want to know more about it, you can go to their website and learn more about it. So now we've learned CAM, Wacom, and Wacom X. How about we compare Wacom and Wacom X? The most obvious difference is Wacom X covers entire atmosphere, and Wacom is just high top version of CAM. And they have so many different factors. You can compare the table in the middle and to the right. They have different number of vertical levels. And Wacom X only comes in 2-degree horizontal resolution, but it has shorter time step, only 5 minutes. And the chemistry option, there's only one chemistry option, but I know this is evolving as we're working on newer version of CESM 3, so Wacom 7, and Wacom X used to be based on CAM 4 and Wacom 4, which was older version, but the newer one will be based on Wacom 6. Now you learn enough about Wacom. Now you want to run it already. You're a really fast runner. So when you want to run a model, there are a couple options. Each component has different options. So in the table on the left has 4 different colors and 4 different components. There's atmosphere, ocean, land, and sea ice. So each component has option. Hey, you want to turn it on as interactive, or you don't want to turn it on as interactive. So let's look at the yellowish box on the upper left-hand side. I added red square around it. So Wacom can be run with either interactive or specified chemistry. You don't care about much chemistry, then use a specified chemistry. And if you care about chemistry, you use interactive chemistry. And same thing with dynamics. Free running means Rebecca just explained very well about this, that the model just run has its own dynamics. But when you want to compare your Wacom output to actual measurement, you can't really compare with free running and actual atmosphere because this is not right. In that case, you either nudge the model. Nudging is you just maybe elbowing someone, keep nudging it. Hey, don't do this. So keep adding forcing from the outside. We used to call it specified dynamics using this MERA2 or GEOS5 reanalysis data to use as an input, but I think we're using more nudging approach to just keep the model status too close to the real atmosphere. So now you're almost a runner. And then when you are about to run the model, you need COMSET. So there are multiple different COMSET, different levels. Are these scientifically validated, or is that just development? Can you use it? So we have those scientifically supported Wacom COMSET on the website. You can go look at it. F stands for CAM standalone, interactive atmosphere land. I know you already know about this, and fixed SST and CS610. and pre-industrial and historical run and present day or SD run and so on. And these are the chemistry that can go into WAGM. There's T1 is comprehensive troposphere chemistry, TS1, TSMLT1. Now you already know about this. And WAGM X COMSET look like this, a little bit simpler, but F means F COMSET and X is WAGM X and historical, present day, and SD. Now, I'm going to spend a little bit of time or rest of my time talking about science. Why do we have model? We want to do cool science. So first thing I want to talk about is the quasi-biennial oscillation in the stratosphere. Some of you might know about this, some of you don't know about this. So it's zonal mean zonal wind in the tropical stratosphere. Easterly, westerly wind is propagating downward with average period of 26 months. And global climate models have had difficulty actually simulating it for a long time until pretty recently. One key element in simulating QBO successfully is, as I wrote on the upper right-hand side, there's adequate horizontal resolution, but vertical resolution is the key. We need high vertical resolution and realistic simulation of some convection and waves that makes QBO looks right. That's the figure on the top. X-axis is time, y-axis is altitude. This is WACM 110 level version. And if you look at the bottom one, 70 level version, and the QBO doesn't look as good as the top one. I think I'm running out of a little bit of time. Okay, so next one is important. I'll just go as far as I can go. So in the stratosphere, water vapor is important because it affects radiation, even though stratosphere is very dry. So there's one feature we know of is called tropical tape recorder in water vapor. It came out in 1990s. In 1990s, tape recorder makes sense. Now tape recorder doesn't make any sense. What is it exactly? So the idea was in the tropical lower stratosphere, temperature controls the amount of water vapor going into stratosphere because it's so sensitive, water vapor is so sensitive to temperature. So every season there's dry phase, wet phase going into stratosphere. And in addition to seasonal cycle, there is annual variability, such as this volcanic eruption called Hanga Tonga. Many of you might have heard about this Hanga Tonga eruption. The volcano was a submarine volcano. Because of that, it injects so much water vapor into the stratosphere. And top figure is a time altitude plot of water vapor mixing ratio from microwave limb sounder. This is NASA satellite, this observation. And actually, WACM can simulate Hanga Tonga, just like the reality. It's a figure at the bottom. So we were really excited about this. And now I'm going to introduce you some papers that were published recently to give you an idea. Oh, I want to do those research. Looks really cool. The first one is about Hanga Tonga eruption and its impact on chemistry, because we just talked about Hanga Tonga eruption. By putting more water vapor into the stratosphere, it changes the chemistry, and the ozone decrease was happening in southern hemisphere because of this extra water vapor. If you're interested in, you might want to go and read about this paper. I'm just going to just leave it as it is here. And next one is the QBO. So if we have three different kinds of simulations, we can look at pre-industrial or historical or present day or future. So what would QBO do with the future climate? We know what future climate will look like, and they did some simulation for future climate and what would QBO do. And this figure is a long time series of zonal mean zonal wind in the troposphere. As you can see in the earlier, maybe the cycle is going slightly slow, but it gets really fast. So take-home message from this paper is that with climate evolves with hotter and more convection, and then QBO becomes more annual. This is really important. And why is it faster? And the gravity wave is more active because more active convection. You might want to go and read about this paper if you are interested. And the other one is, so Nick Davis last year, he published a paper. Okay, Wacom looks cool. It goes up to high altitude. I want to do science. But since we have more vertical levels, more chemistry, and then it gets expensive. Expensive means it's not that you're paying from out of your wallet. Computational time takes longer, it's harder to run. You want to look at 10-year simulation, if it takes 10 days, it's too slow. So what Nick did was, instead of using 1 degree nominal resolution model, he used 2 degree. What does that do? And it turns out 2 degree was doing pretty well. Unless you're really interested in really detailed chemistry in the troposphere, you can use 2 degree. It's much cheaper and faster and do your science. Now it's this Wacom X. So I thought it's fair to include Wacom X, even though I'm not a Wacom X person. I read this paper, tried to read it 5 times. I just couldn't figure out what it is. So I put one figure here and a couple sentences from the abstract. So space weather has big uncertainty because of how the forcing is prescribed. If you have more questions about Wacom X or this paper, you can ask Nick and Shu, and it's listed at the bottom. So I struggle with, okay, I just want to understand, I just can't understand, but I tried. So this is a little bit about chemistry. And when they looked at some nitric acid trihydrate, NAT, and look at the high latitude region, and I don't really know about this well either. And the next one is about geoengineering. This is very important. There are a bunch of papers that are written by different people about geoengineering, putting more aerosols in the stratosphere. What would that do to the climate? So this is really important. If you want to learn more about it, go to our website and ask people around. So this is my last page. Then what do you want to do with Wacom? So Wacom is greater vertical extent of atmosphere. We have chemistry and aerosols, middle and upper abstract physics, and coupling of just all kinds of cool things. And because of that, we collaborate. ACOM, CGD, HAO, even outside collaborators, we work hard on making Wacom usable for bigger community. So now the truth comes out. So I'm relatively new to this position. So if you have a question, just go to this maybe website, try to figure it out. And if I cannot answer it today, you can write me an email. I try to get back to you. Or anyone in the audience might have an answer for you. Sorry, I ran over time. So thank you. So we're done. Yeah.
Yeah. Then
2 minutes.
Yeah. No, it's fine. Yeah, we have a few more minutes, but yeah, any quick question? And again, Mijang is new in this, then she might not be able to answer everything right away, but we will find out the right person to answer this.
Yeah,
then.
yeah.
I
So-
can never answer any question right away.
No.
No, I just.
But you can, please ask questions.
Yeah.
I didn't want to intimidate you not being able to ask questions.
A great talk. So I have a question about the Hunga eruption and then about the QBO prediction. So the Hunga eruption basically part of the QBO in 2022 and 2023. So when we are predicting the QBO for like next year or say 100 years from now, we don't incorporate any volcanic eruption in that, or do we?
So I believe there were a couple of papers looking into the connection between Hanga eruption and the QBO because this water vapor changes radiation and QBO changes the wave dynamics is related to QBO. I don't know much about it. So I want to know more about your, so let's talk after the session.
Sure,
Your question was not so clear to me.
Yeah. Any more question? Yeah.
Hi, thanks for the introduction. I'm very curious about the radiation in WOCAM, so I'm wondering if there's any comparison, especially about the radiative fluxes at the surface or TOA, that like is much more similar to observation in WOCAM than CAM.
So top of atmosphere, I don't know what does CAM do in terms of radiation.
Sorry, I was running around and I didn't
so
listen to
Oh
the
yeah,
question.
I can repeat my question.
Yeah.
So I'm wondering if there's any comparison of the surface radiative fluxes or TOA radiative fluxes between the CAM and WOCAM, or which one is better?
When we have, then when you look at the top of the atmosphere in balance in CAM on WACAM, usually we have to tune the model. When you do, we will talk about this in my presentation tomorrow, but you have always to adjust the top of the atmosphere in balance to avoid to have a runaway simulation. Then sometimes you will have tuning, and we will see what it is tomorrow, but it can be different in CAM and WACAM to be able to have a stable simulation.
Then how about the surface?
And the surface,
I don't know how.
Yeah, because I feel WACAM is more up there. I feel the surface. I'm not a WACAM specialist. I never run WACAM in my life.
If you can talk more about it, you can tell me more exact questions and maybe I can find something.
Okay. Yeah, sure. Yeah, thanks.
Yeah, thank you. Any more question? Last question, okay.
Both talks mentioned using nudging to have a more realistic atmosphere rather than using reanalysis products. And I was wondering what the benefits of that are. Just could you expand upon that?
Rebecca, you want to answer that? Yeah? Just
use microphone.
help yourself.
So, can you hear me? Is this right?
Yep.
So the question was why would you use nudging rather than just putting in the reanalysis and saying these are the exact wind fields? Is that the question? Yeah. The reason is because you have other physics happening in the model and you really want to keep that consistent with your model. So like local convective situations as well. You can actually nudge the model 100% towards reanalysis, but then you're going to get these, say you have 6-hourly reanalysis fields, you're going to have this shock to the system and then relaxing back to the physics in the model and shock to the system. So you really just want to nudge the model towards the reanalysis to have the best balance between reality and what the model you have, the physics in the model you have is doing. Is that answering your question?
Yeah. What's the timescale that you use for the relaxation?
I'm not sure. I'd have to look that up. I think it's... Yeah, I'd have to look that up. I want to say 12 hours, but I don't know. Yeah, there's definitely adjusting in the hourly. Like there's a time adjustment and then there's a percent adjustment. But we'd have to look that up. But let us know and we can look up those exact values for you.
Thanks.
Okay. If there is no more question, we can thank one more our morning presenter. Thank you. And then we will move to the coffee this time and donuts. then. Oh, I see. Yes, we are going to introduce the next lab session, and we are going to have multiple people speaking, introduce briefly this section. Then basically this is a reminder. Today we are going to do what we call the challenge exercise. Then so far you have run the couple model, but then in the challenge exercise, you can run the atmosphere or paleo simulation, atmospheric chemistry, land, ocean, sea ice, land ice, and biogeochemistry. Again, this is a self-paced lab. If you feel you're not ready to do this, you can work still on the section that you have worked before. In the library, we have create area. You will have the atmosphere, paleo, and atmospheric chemistry will be in the main area. We count people, and it was the main people there. And then land will be in one of the little library area that's on the back. They will be signed. Sea ice and land ice, I think they are in the diamond room. But Elizabeth put sign, and when you are there, we will see where she has put the sign. And so that you can put a face on the different helper, then I will be helping with the atmosphere, but they will be as a helper. Sophia, she's here, then she will be helping with the paleo exercise. Gunther is not here, but we have Kate here that will be helping, and Gunther might be here too. Then Dave will help with the sea ice. Then Rebecca and Mijong, they will help with chemistry and WACAM. Eric is not here, but he will be helping with the land. He will be in the library. Kristen is here, and then Alpe, Kristen with the biochemistry, and Alpe with the ocean. Okay, then we are going to give you briefly an overview of what you will, the type of exercise that you will have in each section, but you are not stuck in one section. If you want to do one exercise in the ocean and after move to the biochemistry, it's fine. You can move between different groups. We will stay in one area, but you are the one moving. Then this is for the atmosphere. Then so far you have run the fully coupled model. Then this is when you have all the components that are active. And it's what we call a B case. I don't know how to use this thing. It's what we call a B case, but we will do a F case. It's when you run the atmosphere only. You have also to run the land at the same time, but you will use like sea surface temperature for the ocean, and for the sea ice, it will be prescribed sea ice. And we have a few exercises that we propose. We will use historical SST forcing instead of using fixed forcing. So far in the run, you are repeating a single year, the year 1850. Here we will use historical forcing that vary year to year. You will see how to change the starting date. Also, we will have a few exercises where you can increase the orographic height over the western US. It's the top plot on the right. Then you can make the mountain there higher. Or you can also modify the sea surface temperature in the tropic. And the last exercise, we will trigger a threshold of deep convection over land. You will not have time to do all of this. You pick the control and then one of them, and then, but they are there later if you want to do this. Then the next one, it's paleo. Then I'm going to give microphone to Sophia.
Yes. Okay, if you're interested in paleo, today you could learn how to modify the orbital parameters in CESM. So you might have heard of Milankovitch cycles, and so this is an important long-term control on climate in the past. And today we're going to run a mid-Holocene configuration with just the orbital parameters, but we can talk about other things about the mid-Holocene if you want. And then also, we're going to teach you how to run a CESM simulation with water isotope tracers, if you're interested in that configuration, and then show you how to plot the isotopic composition of precipitation.
Thank you.
Yeah.
Then for the chemistry.
Yeah, so we have three experiments to run with chemistry today. One is a control run, just running chemistry out of the box from the model. You can either choose to run ChemChem or WACCM. And then two tests. One is changing a reaction rate in the chemical mechanism and seeing how that impacts ozone. And then another test is to change emissions. And that's actually much more complicated than it sounds. There's a lot of things you have to think about when you're changing emissions. And then there's this bonus visualization using a specific tool, a kind of quick look tool that we have. And we also have Danny Lung coming up, the developer of Dust. He's also the Dust scheme, he's gonna come up and help for the session as well.
Okay. Somebody didn't do the homework. Yeah, then in the land exercise, you will learn something about the land. You will see. No, sorry. You will, go in the webpage and there will be a description of the exercise over there. Then, then the ocean. Yes.
For the ocean, we'll run the GCOM set, and the GCOM set is where we couple POP ocean model with the sea ice model and force them with the normal year forcing data atmosphere. And so we'll first run a control case, no changes, the default setting, and then we'll make several changes and then visualize how those changes affect the simulation. So in the second exercise here, we will turn off this overflow parameterization. In the third one, we will play with the wind stress. And optionally, if you're interested in the BGC or ecosystem, there's this fourth exercise where you can turn on the ecosystem mode and see how it changes things. And then another extra exercise is the MOM6 exercise where, so as you know, MOM6 is the new ocean model that will be standard in CSM3. So you'll have the option to download a new CSM version, including MOM6 as the ocean component, and run a control case using MOM6.
Okay, then for the sea ice.
Sure. So similar to what Alper just talked about, we're also going to look at a GCOM set. So this is just coupled sea ice and ocean. I think we just do this so-called normal year forcing where we repeat the forcing for the same year over and over and over again. But that will be our control simulation. And so it'll be similar to the ocean there. But then what we're going to do differently for the sea ice is we're going to adjust the sea ice albedo. And we're not adjusting albedo directly. We're actually adjusting a parameter called the snow grain radius. And so that's something you can learn about. And then we'll also see the sensitivity to snow conductivity as another possible tuning parameter. And you can see here in the pictures, you can see that the albedo might have a big impact in your simulation. So just look for that. And then a little sneak preview to tomorrow, you're going to learn how to do some polar projection plots. And so if you're really just running through this very quickly, then maybe you can get a start on tomorrow's exercise and do some polar projection plots. So.
And land ice.
Hey, everybody. So the land ice model here in CESM is called CESM, and it's actually one of the newest components that we've added to CESM and probably what you call the most experimental at this point. So one of the things that you may have seen, the B cases that you've run so far that have been all active have actually had a stub or an active land ice because we still haven't got it exactly where we want it to run with a full model yet. And so what you guys are going to do with the challenge today is that you're going to run what's called a TCOM set, which is more of the workflow that we use for the land ice, where you take the forcing from a BCOM set where you've run with inactive glaciers and you apply it to a COM set with only active glaciers. And so we're going to run that TCOM set and take a look at how the climate forcing impacts the Greenland ice sheet in an active situation and calculate the sea level rise from that. So it'll be fun.
And last but not least, biogeochemistry.
Okay, for the biogeochemistry exercises, we're not actually going to run the model, but just set up two different cases and compare the case directories, and specifically the name lists. And so we have two comp sets, and they basically are different in the way that CO2 is handled. So one of them you have prognostic CO2, and one is diagnostic. So the prognostic one is more of an emissions-driven kind of case, so where you actually emit carbon to the atmosphere and then let that carbon evolve with the sources and sinks naturally. And so this is predicting CO2 concentrations in the atmosphere. And the other one is the diagnostic CO2, where this is more like a concentration-driven mode. And this is where we prescribe atmospheric CO2 concentrations, and those are read from a file. So yeah, I included a little schematic over there to kind of, that's the emission-driven scenario when the really carbon is left to flow around freely in the Earth system. So that's like the real Earth system model mode, I would say. So yeah, so you'll just look at the differences between the case setups of these two different cases.
Yeah, then I think it's all we have for you. Yeah. Then if you have any question now, more general question, ask it now. Otherwise, specific question, maybe let's keep it for the library. Then once again, oh yeah, then wait, general question. And once again, you can keep working on previous exercise if you're not ready to move to this.
Is the biogeochemistry adjusting the ocean biogeochemistry or the land biogeochemistry scheme, or both?
No, I mean, those things are the same. It's just how the CO2 interacts with the, like, so it's prescribed CO2 concentrations for the diagnostic one. So that just holds them at historical values in the atmosphere, whereas they're still being absorbed by the ocean and exchanged in that way. It's just kind of one-way exchange rather than two-way.
Okay.
Does that make sense? Or we can discuss it more.
Okay, we'll discuss it more.
I think there was a question behind. No, okay. Okay, any question? Okay, then let's move to the library, start to work on this. Maybe there are still donuts, I don't know. Then we are going to have our next speaker, Bill. There are people coming. Oh, there are a few people coming. Okay. Yeah, then our next speaker is going to tell us more about the land ties. You should give me your trick to make them quiet. What do I say? No, I want to see the trick.
Seems like they're still coming in.
Okay, are we ready to learn everything about land ice? Then it's really an effort that's really special here into Anchor. And Bill is going to tell you more about it.
Can you all hear okay? So maybe a little more sound? Okay. Okay. Hi, everybody. My name is Bill Lipscomb, and I'm one of the team here that works on land ice modeling. If you're not familiar with the term land ice, it's a term that includes pretty much anytime snow falls from the sky and does not melt in place, but turns into ice under its own weight and starts to flow. That's what we call land ice. So it includes the two large ice sheets that we have today in Greenland and Antarctica, as well as all the smaller bodies of ice, which we call glaciers. And that's to be distinguished from sea ice, which you're also hearing about this week, which is ice that forms directly in place on the surface of the ocean. So I'll give you today, the first part of the talk will be just introductory material on glaciers and ice sheets and why we care about them in terms of sea level. Then I'll say a little bit about the history of ice sheets and CESM, going back to CESM 1 through CESM 2 and now the new CESM 3. And I'll give you a few research highlights and talk about what we've been doing in the last year or two and where we're going. So you're all aware that global sea level is rising. Sea level has been rising since about 1900, but especially quickly in the last 3 decades or so. Since 1993, we've had satellite altimeters measuring sea level very accurately. And this shows the increase in global mean sea level since 1993. We've had about 10 centimeters of sea level rise in that time for 3 main causes. Those being thermal expansion, ocean water warming as it expanding as it warms, glaciers outside Greenland, Antarctica, and then the 2 ice sheets. Before 1990, the ice sheets were close to mass balance, and so they made a very modest contribution to sea level. But mass loss from ice sheets has accelerated, and so now ice sheets account for 30 or 40% of ongoing global mean sea level rise. And when I say global mean sea level rise, I mean just that, the global average. But sea level rise is very unevenly distributed around the globe. So for instance, on the right is a panel showing sea level or changes in sea surface height measured by satellite altimetry. And you can see there's bands with much higher increases in height and some regions with lower. This is largely because of changes in ocean dynamics. But other things that explain why sea level would rise more quickly in one place than another include local causes like land subsidence. Also, there's still some glacial rebound going on from the last ice age, which causes regional variations. And interestingly, when an ice sheet loses mass, because it has less mass, it has weaker gravity. As a result, the nearby ocean tends to flow down away from the ice sheet. And for that reason, somewhat ironically, if you lose lots of mass from Antarctica, you actually have sea level fall around the Antarctic coast and rise away from Antarctica, and then a similar effect for Greenland illustrated here. Most of the world's ice is locked up in these 2 ice sheets. If you melted all the ice in Greenland and put it in the ocean, you would raise global sea level on average by about 7 meters. The mass balance in Greenland is incoming snow that doesn't melt and turns to ice, which leaves the ice sheet typically in one of 2 ways. One is it flows to the coast where it's warmer in the summer and it melts and that meltwater flows into the ocean. And the other is, in some cases, glaciers reach all the way to the coast, and then that ice calves as icebergs. When the ice sheet was in balance, those two processes were about equal. About half of the mass increase was balanced by calving and half by surface melting and runoff. Over in Antarctica, you have about 58 meters of sea level equivalent, much more than Greenland. And there's very little surface melting in Antarctica, so all the snow that comes in, a lot of the ice flows onto these floating ice shelves, notably the Ross ice shelf and the Filchner-Ronne ice shelf and some smaller shelves. And that ice either calves off as icebergs at the calving front, or else it's melted from below by relatively warm ocean water. Both ice sheets are losing a lot of mass. Greenland about 270 gigatons per year, which is enough to raise sea level by about 3/4 of a millimeter each year, and then 150 gigatons for Antarctica. The rest of the world's ice is mostly locked up in mountain glaciers. That's not nearly as much ice. If you melted all of that, you would raise global sea level by about 40 centimeters. But the contribution to sea level from glaciers is comparable to that from ice sheets, about 230 gigatons per year. And that's because a lot of these glaciers are in areas where they're very vulnerable to climate change, either terrestrial regions like the high mountain Asia, where there's been a lot of warming, or they're exposed to warming ocean waters. And you have a lot of small glaciers like in the Alps, which don't have a lot of mass, but you have in the Arctic and Antarctic regions, you have more of these large ice caps, which contain a lot of the ice that's wrapped up in glaciers. And if you lose glaciers, you not only raise sea level, but you can threaten water supplies for people who rely on seasonal meltwater from glaciers. And also you have hazards like glacier outburst floods. So the way a glacier moves is it always has the minimum speed at the bed and then the maximum speed at the top. And you can think of it as a very, very viscous fluid that just creeps downhill. In the interior, you have this vertical shear so that it might be flowing a few meters or tens of meters faster at the surface than at the bed. But glaciers that are moving fast invariably have water at the bed, either a thin layer of water at the bed, or else they sit on top of a weak till, which is saturated, and so that till itself deforms under the weight of the glacier. And so if the ice is frozen to the bed, the glacier is going to be slow moving, maybe a few tens of meters a year at most. But if the glacier has water at the bed, it can flow by hundreds of meters to several kilometers per year. Depending how it moves, it might be well described by the so-called shallow ice approximation, which works well if the sliding at the bed is slow, or the shallow shelf approximation if it just moves it as a unit, like if there's little or no friction at the bed. And then there are equations, the most accurate ones that people usually use are called the Stokes equations, that combine these two modes of flow in an accurate way. So the mass balance of an ice sheet is just the difference between how much snow comes in. A little bit sublimates, but most of it lands somewhere cold and accumulates and gradually turns to ice. And then you have loss from the processes I've mentioned, melt and runoff, which is important for Greenland, and calving and basal melting, which is the dominant source of heat loss for Antarctica. And in a balanced climate, these things are equal over the long term. But when you have more mass going out than coming in, of course, you get mass loss and sea level rise. This is a plot showing the coevolution of carbon dioxide, global mean temperature, and sea level over the last 400,000 years as deduced from paleoclimate records like ice cores. And what it illustrates is these 100,000-year cycles that ice sheets play a very important role in. So between the last interglacial, about 125,000 years ago, and the last glacial maximum about 20,000 years ago, and the present day, and then the recent increase in carbon dioxide, you can see that temperature's been changing more or less in step with carbon dioxide. Without humans involved, those two things evolved together for complex reasons. But since 1900, it's been CO2 driving temperature increases. And the huge sea level changes associated with those temperature increases are mainly because of large northern hemisphere ice sheets that grow and grow and grow until the North American ice sheets and Eurasian ice sheets peaked about 20,000 years ago, and then fairly rapidly melted. bringing sea level to close to present day levels. In past warm climates, ice sheets have been much smaller than they are today. So for example, 125,000 years ago, which was the last time we had a climate that's similar in temperature to today's, global sea level is thought to have been about 6 to 9 meters higher because both the Greenland ice sheet and the Antarctic ice sheet were smaller than they are today. Here's a guess as to how big the Greenland ice sheet was. The last period that was significantly warmer than today was the Pliocene, about 2 or 3 million years ago, when it's thought to have been perhaps 3 degrees Celsius warmer than pre-industrial. And CO2 was at 400 parts per million, which is about what we have today. So you might guess that if CO2 stayed at present day levels, eventually ice sheets would evolve to where you had sea level. We don't know exactly how much sea level was higher at that time, but perhaps up to 10, 15, maybe up to 20 meters, which implies that most or all of Greenland melted and probably a big chunk of West Antarctica, this part here, with this other part being East Antarctica, which is generally higher and colder and less susceptible to climate change, even large climate change of several degrees, except that it is thought that this part of East Antarctica, where you have a lot of ice that rests below sea level and is vulnerable to the ocean, that may have melted during the Pliocene period. But the part of Antarctica people worry most about is the part that flows into the Ross Ice Shelf and the Filch-Narani Ice Shelf and into the Amundsen Sea, which, because it's sitting below sea level, is exposed to the ocean. So if you have any significant ocean warming, that ice is very vulnerable to melting and sea level rise. And that may have accounted for a lot of the sea level rise at this time, and people worry that it will account for a lot of sea level rise in the future. So, as I mentioned, the reason for this instability, potential instability, is that most of the ice is grounded below sea level. And that allows for this feedback where in the Southern Ocean, unlike the tropical ocean, you have typically colder water sitting on top of warmer water. The warmer water is saltier, and that's why it sits below the surface water. And if the top of the warm layer, called circumpolar deep water, sits above this sill, then you have an avenue for warm water to reach into this ice shelf cavity. And once it does that, it has access to the grounding line here that divides the grounded ice from the floating ice, and that can drive retreat. And in this particular illustration, you can see that the bed slopes down as you go into the ice sheet interior. And because of reasons of ice sheet dynamics, if the ice is thicker as it retreats, it will flow faster, and that's a positive feedback that will lead to further retreat. So this feedback is called the marine ice sheet instability, and is one reason that people worry that the West Antarctic ice sheet could potentially retreat, such as to raise sea level by a meter or more on timescales of a few centuries, as opposed to millennial timescales if this feedback were not present. A region that's particularly vulnerable to this feedback may be the Amundsen Sea embayment, which is where the Thwaites Glacier and the Pine Island glaciers, which you may read about in the papers a lot, those glaciers are both retreating a lot today, and it's mainly because they're exposed to this warm circumpolar deep water just off the coast. So you may be familiar with these. The most recent sixth assessment report of the IPCC projected that global mean sea level will rise by 28 to 55 centimeters by 2100 optimistically under very low emissions, and 63 centimeters to about a meter under high emissions. So a lot of sea level rise is already baked in, either because the ocean is still going to be warming for a few decades, or because ice sheets and glaciers have not yet adjusted to steady state with temperatures as they exist today. But obviously, there's a lot of melting that can be prevented by large and soon emissions reductions. These likely ranges, the AR6 pointed out, specifically don't include some processes that are deeply uncertain. The marine ice cliff instability is one that people aren't sure if it's a real process to worry about or not. And also, there's a lot of uncertainty about ice shelves melting below because of ocean changes, since that's something that's very hard to model and measure. But our best guess anyway is that sea level rise would probably not exceed a meter under a high emission scenario. But this is still quite a lot of sea level rise for sea level communities to have to adapt to. So now about ice sheets and CESM. We're one of the newer components of the model. Back in the old days when it was called a community climate system model, it was an atmosphere, ocean, sea ice, and land surface model primarily. But then with CESM 1, which was the first so-called Earth system model that this community created, a lot of new components were added, including biogeochemistry, and one of those was ice sheets. And it's really hard to put ice sheets in Earth system models, mainly because ice sheets have dynamic boundaries, and that changes assumptions about fixed boundaries between atmosphere, ocean, and land, which previous versions of the model had already assumed. But we're gradually going about relaxing these assumptions and coupling ice sheets to other components in a dynamic way. It's important to know, if you're interested in ice sheets, that the surface mass balance of ice sheets, that is the difference between the accumulation from snowfall and the ablation from surface melting, is not computed by the ice sheet model, the community ice sheet model, CESM, but by the land model. And so we had the land model, which has a state-of-the-art snow and ice model communicating with the atmosphere on hourly timescales. That computes the accumulation of snow and ice and the melting of snow and ice. And what we do is on the relatively coarse land grid at 50 to 100 kilometer grid scale, we have multiple elevation classes in each grid cell. And by having these different elevation classes, we can represent greater melting at lower elevations than higher elevations. And we take that information, we pass that to the ice sheet model, CESM, on a finer grid. And so on CESM's fine grid, the elevation class information is downscaled to a scale of around 4 kilometers. And then we do some calculations to make sure we're conserving global mass. And then that's what the ice sheet sees. In the first version of CESM, we used so-called shallow ice dynamics, which are not very accurate for fast-flowing ice. And we only had one-way coupling, meaning that the climate affects the ice sheet, but not vice versa. So in CESM2, we worked to improve both of those simplifying assumptions. First, we implemented interactive coupling between the Greenland ice sheet and the land and atmosphere. Interactive meaning that not only does the ice sheet see changes in climate, but the land surface sees changes in the ice sheet. So when the ice sheet retreats, say, then it returns its reduced area and elevation to the land model. And the land model, which has different surface types, including glacier surface types and vegetated surface types, it can go back and forth between. So for instance, if you lose ice around the edge of Greenland, that'll turn into some sort of tundra. So it's vegetated or bare land instead of being ice covered. And every once in a while, we'll not only update the land surface, but also the atmosphere's version of the land surface. So just to schematically illustrate the coupling, we have the ice sheet model, which is responsible for ice sheets moving. And we have the land surface model computing the surface mass balance, which tells the ice how much they're growing or melting at the surface. And these communicate through the coupler. Also, when an ice sheet, when ice calves from the ice sheet model and the ice sheet loses mass, that mass has to go somewhere. And so it's fed into the ocean. The coupling we're missing primarily in CESM2 is coupling whereby, let's say if the ocean warms, the warmer ocean temperatures reach the base of ice shelves and can cause the ice sheet to retreat for that reason. So that's something we've been working on for CESM3. I'll give you a few research highlights from CESM2 though. We were active participants in the ice sheet model intercomparison project for CMIP6, also known as ISMIP6. We were one of a number of ice sheet models that contributed projections for both Greenland and Antarctica. Just to summarize these quickly, these projections were made using standalone ice sheet models, meaning not coupled to a climate model, but receiving input, climate input, like warming, that was derived from climate or a system model output. And the general message is that climate models predict more melting on the surface of Greenland, and that leads to, by the year 2100 and higher emissions, about a 10 centimeter increase in global mean sea level, plus or minus about 5 centimeters. For Antarctica, however, the models are all over the place, and that's because the models disagree about how much the ocean is going to warm and how much that's going to affect ice sheets. So in West Antarctica, you generally have sea level rise due to ice sheet retreat, but the numbers all over the place. And East Antarctica, somewhere close to balance, depending on whether you have more snowfall due to a warmer atmosphere, which would lower sea level, or ice loss from some parts of East Antarctica. We did coupled experiments with an interactive Greenland ice sheet. In order to do this, we need a good surface mass balance for Greenland. And this illustrates in the left panel the surface mass balance from a regional Arctic model called RACMO2, which is calibrated against observations. And so this combination of high resolution model and observations gives us the closest thing we have to truth, to what's really going on in Greenland. And then here's what the model does. And you can see that overall the patterns are pretty good. Blue is accumulation, red is ablation in these narrow bands along the coast. But the biggest bias we have is too much snowfall in the southern interior. And that's mainly because our mountains here in the southeast are not very well resolved in a coarse resolution model. And so we tend to have too much snowfall in the interior instead of it being concentrated in a band of the coast. And that seems to be mostly resolution related. So that's a bias that's hard to get rid of. When we did couple simulations, fully coupled in high resolution scenarios, I guess what happened is not so surprising. Apologies for the flip in colors. Here blue is ablation and red is accumulation. But these bands of melting on the coast widen. So by the end of the century, you have very wide bands of net ablation, and that leads to a large increase in sea level. So you have about 110 millimeters, 11 centimeters of sea level rise from Greenland by 2100. Although, interestingly, this doesn't lead, at least in CSM, to huge differences in the overall climate response that we don't see, for example, the meridional overturning circulation collapsing. But we do see this very significant change in how much ice there is in Greenland. We've also done these simulations for past periods. This is for the last interglacial, about 125,000 years ago. So starting at 127,000 with a Greenland ice sheet, which is all there, if we force it with the warming climate that happens over the next 8,000 years, you have orbital forcing parameters that, that lead to, at least initially, to Greenland being quite warm in the summer, so having a lot of summer melting. So the ice sheet shrinks to a minimum by about 121,000 and then very slowly starts to regrow. An interesting thing we learned in these simulations is that you don't see nearly as large a response unless you include vegetation, which in these simulations is updated every 500 years to reflect changes in ice cover and other changes in the climate. More recent work on Greenland deglaciation, which is sort of inspired by these paleoclimate studies. We think that at the last interglacial, the ice sheet was probably not much smaller than this. And if you'll notice in this plot, the ice is sort of hanging on to high topography in the west. And it turns out in these simulations, once the ice loses touch with this, what you call a pinning point here in the west, it retreats quite rapidly until you have nearly complete deglaciation and only a little bit of ice left in the higher elevation parts of Greenland. And so this suggests a threshold of deglaciation around 3.5 degrees. And beyond that threshold, you lose the pinning and you get nearly complete deglaciation of the ice sheet. But this does take place over a time scale of thousands of years, so it's not an imminent worry, but something that's helpful in understanding why ice sheets do what they do during warm periods of different duration. So now I'll shift over to what we're doing for CESM3. So the ice sheet model that will be released with CESM3 is called CESM3, will be called CESM3. And we went into the process with several goals for both the ice sheet model and the coupling of the climate model. So for the ice sheet model, we wanted to improve the physics of the model. In particular, the treatment of basal sliding along the bed of the ice sheet, and the treatment of water or hydrology at the base of the ice sheet, because that interacts with the sliding, and also iceberg calving, which we had a very simplified treatment in CSM2. We also want to do a better job initializing the ice sheet, because what you initialize the ice sheet to will largely control what happens in the next 100 years or so. And something I'm really excited about is simulating mountain glaciers and not just ice sheets. And on the coupling side, we wanted to improve, or at least not make worse, the biases in Greenland surface mass balance, which I mentioned already. and also support coupling, interactive coupling, not only with Greenland, but also with Antarctica and with paleo ice sheets of interest, such as the large northern hemisphere ice sheets from the last ice age cycle. So in terms of hydrology, we've put in a sort of intermediate complexity hydrology model where it's not so detailed that it's very expensive, but it's efficient to run. And with that, we can do a pretty good job of simulating water channels at the base of the Antarctic ice sheet, as well as Greenland. And then some early work using this hydrology model showed that at the time of the last glacial maximum, where you had this big ice sheet over Canada and part of what's now the US, there are parts of the ice sheet where the hydrology is really important and how the ice dynamics evolves, and other places where it more depends on the topography or on having a weak basal till that largely determines where the southern margin is. But that combining these things, the hydrology and the till, allows you to predict where ice streams should have been, and it turns out it agrees pretty well with where ice streams are known to have existed from paleoclimate evidence, which is nice. In terms of iceberg calving, there's a lot of ice model and comparison projects that are going on at a given time, and one of the new ones is called calving MIP. And so what we do for calving MIP is we set up this prescribed calving rate on a prescribed geometry, and we see how our calving front retreat compares to other models' calving front retreat, which it compares pretty well. So that assures us that our basic model numerics is working correctly. And then with those numerical improvements, we try putting in actual calving laws, which would be a physical rule for taking what you know about the ice sheet, its thickness and its internal stresses, and trying to prognose where the calving front should be. And we've recently come up with a calving law, sort of a rule for how to predict where the ice will calve, that gives you calving fronts as illustrated here, where all the yellow ice is the ice that's floating. And then compared to observations, to first order, the agreement is quite good. So we're excited about that. This is an artifact of the way we've initialized the model. That's Thwaites retreat, but that's not something to worry about in the real run. One reason that ice sheets are hard to initialize is that the present day ice sheet is not in steady state. Well, ice sheets are never exactly in steady state, but 100 years ago they were much closer than they are now. But nowadays we have satellites that tell us how the ice thickness is changing in different parts of Antarctica, for instance. And you can see this large thinning in the Amundsen Sea region. Some thinning, some thickening for ice shelves, some thickening in Queen Maud Land here due to increased snowfall. So a fairly complicated pattern, but notably this intense thinning in West Antarctica. And that makes it hard to spin up a model to steady state. But we've come up with a technique where we can basically compensate for this recent thinning during the spin up and then turn off the compensation when we run forward. And in that way, we can reproduce both the observed thickness and the ice sheet starts evolving correctly when we start running forward after the spin up. And when we do this, we find that, well, if we increase the warming, then everything goes faster. But even if we don't increase the warming, if we don't warm the ocean, we see that the climate implied by the present day melt rates is enough to cause collapse of the Thwaites and Pine Island regions. So there's still some uncertainties here, but definitely concerning that we may already be at a point where the ice sheet is not, strictly speaking, this is not something that inevitably will happen because it depends what human beings do, but possibly if we don't cool the climate, this is where we're headed over a time scale of several centuries. So this is obviously something we want to understand better. For mountain glaciers, we've adapted CESM so that it not only runs as an ice sheet model at a resolution of, say, 4 or 5 kilometers, but it also runs as a glacier model at a scale of 100 to 200 meters. And so we've started applying it to mountain glacier regions. Started off with the European Alps, where there's a lot of data. This is the region around Mont Blanc in France, and this is the Bernese Alps of Switzerland. And this is the Aletsch Glacier, which is the longest glacier in the Alps. And you can see, for example, that if you run the model forward for a century, even if you don't warm the climate anymore, you get significant retreat of the Aletsch Glacier and some other glaciers. And we estimate the Alps will lose about 63% of their volume in the next century even under a very, very optimistic scenario of no further warming, and typically 90% to 100% in more pessimistic scenarios. So this is an illustration of the fact that present day climate implies glacial loss, which hasn't yet been realized, but will be realized over the coming decades to centuries without changes in CO2 concentration. Our surface mass balance for Greenland, CESM3, looks pretty similar to CESM2, where we have these narrow ablation bands along the coast, and then accumulation over the interior, and this interior snowfall bias. It's hard to get rid of that bias, as I said, but overall our surface mass balance is pretty good, about 40 gigatons per year higher than what our best guess from RACMO. Okay, we now have support in CESM3 for running Antarctica out of the box, as you could do for Greenland in CESM2, and also for running multiple ice sheets, 2 or more in a single simulation, which will be a really nice feature. And we're also in the process of finishing up the coupling between CESM and the MOM6 ocean model, which means, for instance, that if MOM6 warms, that warming will be transmitted to the base of the ice sheet. And a lot of projects for the future. Some high priorities are extending our glacier projections to other regions, coming up with a way to better understand what happens in these ice shelf cavities that may not be possible to resolve at the scale of a global ocean model. And also we have a collaborator who has a solid earth and sea level model, also known as a glacial isostatic adjustment, or GIA model, which we would love to couple to CESM and to other parts of CSM so that we can model changes in the distribution of water around the oceans as water is added from melting of ice sheets, and also as the earth rebounds from changes in the load. So just to wrap up, in the CSM2, we had a lot of science and software advances that put us toward the forefront of where Earth system models are in terms of modeling ice sheets, but with a focus on Greenland. And with CSM3, we're very excited to be supporting other regions with ice, notably including Antarctica and paleo ice sheets, especially in North America from ice ages, and also small mountain glacier regions around the world. And while the coupling to the land and atmosphere is pretty mature now, coupling to the ocean is still in its early stages in an area of active research. And largely because that coupling is not so mature, Antarctic ice loss due to interactions between Antarctica and the ocean is and probably will remain for a while the largest uncertainty for sea level rise. And with that, I'll just point you to the people in charge of the Land Ice Working Group. I'm the main model developer for CESM. Gunter Legee is the co-chair and science liaison for the Land Ice Working Group. Maren Biscayno in the Netherlands is the other co-chair, and Kate Thayer-Calder here at NCAR is the software engineering liaison. So Gunter and Kate are people to go to if you have questions, and of course me as well. So thank you, and I'd be glad to take questions for a few minutes.
Yes, thank you so much. Yeah, the question?
Thank you. It was really exciting to hear about land ice. I was wondering if you do like paleo deglaciation experiments, and like how would you constrain the initial conditions in that context?
That's hard. Are you thinking about a particular period?
No.
Well, there's these reconstructions that people do based on paleo data, like I6G is one that a lot of people use now. So let's say we have I6G is what the ice sheet is supposed to look like at 20,000 years ago. And then we want to spin up our model so it looks like that. And so what we would probably do is have 2 or 3 snapshots of the climate over the preceding millennia and use those to make a simple temperature precip parameterization, which we'd apply to the ice sheet model forced offline. And then we would tune parameters in the ice sheet model, trying to match what we see in I6G. But in some cases, we might learn that the I6G is not a dynamically possible ice sheet because it wasn't created based on dynamics. So we might find out that, no, the ice sheet can't be that steep. It has to be more like this rather than like this. And in that way, the paleo reconstruction research and the ice sheet dynamic research can kind of move hand in hand. But at the moment, they're ahead, but we'd like to be more useful in putting constraints on previous ice sheets.
Cool.
Does that answer the question?
I'm really sorry, but what is I6G?
Oh, I'm sorry. It's just the name of, it's an acronym. It's the name of a product which is based on paleoclimate records. And it says, for example, this is how, what we think the ice elevation extent was at a certain period in a certain region.
Cool, thank you.
Question?
Hi, thank you for your talk. What happens to your icebergs after they calve? So where do they melt?
Where we'd like them to melt is we'd like them to break off into icebergs in appropriate size and have them drift in the ocean where they really drift, which might be several hundred kilometers from where they formed. What actually happens in the model, though, is we don't have a size distribution, we just have a mass flux. And then that mass flux is instantaneously melted by the ocean, taking heat out of the ocean. And then there's some smoothing over a certain region that takes place such that we don't dump all the ice into, for example, into one grid cell, where we make that grid cell freshwater because we're putting too much ice in. So, so basically the fresh water and the heat required to melt the water are spread out over some region that you can choose.
Cool, thank you.
I knew you would have a question.
A follow-up to that, is the smoothing that you do, does it take into account ocean currents? Do you try to like put the water where you think the ice would be going, or is it just like spread over a region?
It's just spread over.
Okay.
But it would be, there are groups, for example, GFDL model has an iceberg module, which actually they do attempt to spread it out more realistically.
And does that make a difference that you know
of? My sense is it makes a difference, but not a huge difference, such that you lose sleep over. But it's obviously better to do things in a more physically realistic way.
Okay. And I had another question about how you handle ice, like glaciers melting. Like that's happening at a scale that's much smaller than the scale the models are running. Do you prescribe the runoff that you expect? Like, do you run those regional models and then prescribe that to the fully coupled model?
Like for example, if you're interested in the Himalayas or some region like that,
yeah.
What happens, let's say, to the runoff as the climate warms and those glaciers melt?
Yeah.
At present, those regions are not run as if there were actual dynamic glaciers there, and so the ice mass in those regions is fixed. Which means that it's not done very realistically. I guess what we would like to do is have the mass in those regions depend on how warm it is. And because these are microclimates, it's very hard to model them accurately, or pretty much impossible at climate scale. But you can tune parameters for each glacier region. And this is how we spin up the Alps, is we have a parameter attached to each glacier which says how sensitive that glacier is to climate warming that occurs. And that way, by tuning this parameter, we can spin up the glacier to the right area and volume, more or less. And then we hope that it has the right sensitivity because we've tuned it in that way. And so that's something we'd like to do in the future, and that ultimately could be, we could put that in a coupled run, and then the part of the coupled model output would be changes in runoff, which could be fed to downstream hydrology models. So if you have an interest in that, talk to Summer Manala, who's very interested in that problem and is our main glacier research person now.
Thank you.
Any more question? Yeah.
Thanks for the talk. I'm just curious, kind of when you did your Greenland paleoclimate simulation, why was the vegetation so important in making that simulation happen correctly?
I think mainly because it has an albedo feedback. So when you change the vegetation, you make the surface darker, which makes the atmosphere warmer. And what the ice sheet does is very sensitive to atmospheric warming.
Great, thank you.
Question? Yep.
I just, as a land person, just to follow up to that vegetation question. So like, so every 500 years, is it what it's doing? Is it just replacing it with region appropriate vegetation, or how is that simulated?
It's not done in CSM itself, it's done offline. So we have a, a model called Biome, which was developed elsewhere. And we have collaborators who use that model. And so we run the model for 500 years and we take the output and we send it to them. And they say, okay, given what the new temperatures are, this is how the vegetation should be distributed in a given grid cell as opposed to what it was before. So for example, you might find that as the climate warms, a part of, say, Canada will go from sort of boreal forest to low shrubs to tundra, depending on what the temperature is that the climate model says it should be. And 500 years is sort of a compromise between doing it often enough to keep up, but that's more work because it's being done offline.
And just to follow up, so at the 500 year, it just has the entire succession done for you already?
Yeah, I believe so.
Thank you.
So you shock the model.
More question? Yeah.
I'll follow up to that again. I'm curious if kind of you think there might have been a difference if you hadn't had that shock, or if had done it every 50 or 100 or so years, would you have seen a different result?
That would be a question probably for Aaliyah Summers, who was the lead on the paper. I guess I don't know how much difference that makes, but it's why I really would like to have dynamic vegetation and CSM. Did you have a presentation on the Fates model at some point this week?
Yeah, we did.
So we really would like to have that as happening at runtime.
We have time for one more. Okay.
I have already been, but I was wondering about meltwater and how that's treated, especially in Antarctica, where the meltwater flux is handled by the ice sheet model, and whether it's just like whether it's just applied as kind of a flat flux, or whether it's like interactive.
Okay, are you talking about surface meltwater or basal meltwater?
Basal meltwater.
Like from an ice shelf?
Yeah.
Okay, well this is a new thing because the POP model, which we're moving away from, it doesn't have ice shelf cavities.
Mm-hmm.
It just has a wall at the ice front, and it assumes there's ice where in fact there's a cavity. So, so when we're running with POP, we don't have ice shelves per se, and we don't have any basal melting. So when we're running with MOM6, we have to decide in what cases we're going to turn on the cavities. When we turn on the cavities, we'll have some melt flux that goes to the coupler, and the coupler. So the question is, what does the coupler do with that? To begin with, it'll probably just use some sort of nearest neighbor formulation, where, well, if you don't have if the ocean water doesn't know where the cavity is, you just have to guess where the meltwater goes, and you'll use nearest neighbor. If you do have the cavity there, then you could send it directly to the ocean, and then the ocean circulation would respond to the change in freshness. And so that's the right way to do it. But right now, I can only say we're approaching where we're technically capable of that, but not where we've done the scientific validation where we could say it's actually giving sensible results. So if that's something you're interested in, that's something we want to do. We want to explore in CSM3.
Okay, then we are going to stop the general question here. If you can stick here during the break for 15 minutes, there are some people who don't like to ask the question in front of everybody. It's stressful.
I don't either.
Sorry, I don't either. Yeah, sometimes you are afraid it's a silly question. It's never a silly question. But anyway, then you will stick a little bit, and then we will come back here at 2:15 for climate justice. going. Fortunately, you were not Mike. Yeah, then our next speaker is Monica, and she's going to talk about climate justice.
Does that work? Does that work? Are we good to go? Okay, cool. So I'm Monica Einhorn-Morrison. I'm here in the Climate Global Dynamics Laboratory as a project specialist, and my background is actually philosophy of science and ethics, where the main thing that I look at is, well, I look at the way we build models, how we apply models, whether we're doing that responsibly, as well as how values and the context in which a model is developed impacts its development trajectory and also what it can be responsibly purposed for. So today, though, I'm going to talk to you about climate modeling and climate justice. So overview of my talk is I'm going to give kind of just a broad strokes view of what justice is when we're thinking about that in the context of what we call normative ethics and philosophy. Then we're going to talk specifically about what the themes are when we're thinking about justice in the context of climate change. After we do that, I'll talk a little bit about how, if we're thinking about the science, climate science, justice features into our thoughts about climate science, give a couple example studies of where you see an actual intersection of concerns for climate justice with climate modeling, the way that they've utilized climate models to look at things that have implications for climate justice. And then I'll point out some additional considerations related to some of the things that we're trying to do here in the context of CESM to increase consideration of justice in the context of the science that we're doing with our community Earth system model. So to start off, when we're thinking from a normative ethics perspective, which is just kind of the traditional ethics that if you take an intro to philosophy of class, you'll get exposure to, we have 4 different types of justice that are the different categories that we tie and talk about various sorts of economic, social, environmental, and climate problems within. First type of justice is distributive justice. And I will point out that the distributive justice and restorative justice are the 2 that are most commonly brought into the context of climate change. And we'll think about procedural justice more when we're thinking about the process, scientific process, and the generation of information. But distributive justice here is just kind of fair access to things, right? So we're thinking about fair distribution of resources, benefits, and when we have an unfair or an unequal distribution of things, right, that's a violation of distributive justice principles. Then we have procedural justice, where here we're thinking about we have equity, right, or justice within our procedures, right, for determining some sort of principles, right, some sort of framework or some sort of set of outcomes. And so where you might see this crop up in the context of climate change is when you're thinking about, right, various sorts of negotiations for nationally determined contributions, is that needs to be, right, procedurally just, and that all individuals, right, are getting their say in terms of the process by which we're reaching those conclusions about nationally determined contributions, and there's impartiality involved in, right, what we're doing in that procedure or that process to reach that set of outcomes, especially if those outcomes are meant to be norms that are going to be governing behaviors. Think about, right, emissions allocations in the context of climate change. Now, traditionally, in normative ethics, there was what was known as retributive justice, and I really don't like that word, I just said it wrong, but it's actually been replaced by restorative justice, because retributive justice was kind of an eye for an eye view, where if you harm another person, the equal harm comes to you, okay? And they thought, well, that's not really what we want to achieve when we're responding to harms that a community does upon, right, another community. So now we talk a lot about restorative justice, where it's about repairing harms that a community or an individual, right, may have been exposed to or may have had done to them, but focusing on having recovery and healing in the way in which we respond to that harm, as opposed to some kind of like equal harm done, right, as a result of that harm being begot to them. So when we talk about justice in the context of climate, we talk a lot about unequal distribution So this can be discussed in terms of the uneven distribution of impacts across different regions, across companies, also within different countries or communities, right? So if you look at areas like New Orleans, when it comes to a hurricane, right, uneven exposure to various sorts of impacts, right, flooding, or right, damage to infrastructure from high winds. This would be right, a concern for uneven distribution of impacts when we're talking about uneven exposure to the consequences of climate change. We can also talk about, oh, how weird. Okay. We can also talk about how this is compounded by the fact that a lot of those communities that are vulnerable and are experiencing those uneven impacts or that uneven distribution, right, is affecting them. Those are oftentimes communities or countries that have actually contributed the least to the climate problem to begin with. Because a lot of those countries are ones that didn't have the infrastructure, don't have the infrastructure built up to abuse fossil fuels and emissions in the way that, right, a lot of the global north countries have. And that makes them especially vulnerable. And a lot of the climate impacts that they're experiencing that they're especially vulnerable to compound or are compounded by social, economic, political, and various other sorts of environmental injustices. And then the last one that we think about is we think about policies. And so here's where I was referring to procedural justice, but you can also think about the outcomes of the policies, right? So if the procedure itself fails to be just and fair and impartial, then we can have in terms of the consequences, especially if these are rules or norms for some things like allowances of emissions or allowances for development, right, of infrastructure that might rely on fossil fuels, we can have an uneven distribution of the costs and consequences and benefits, right, of those types of policies that are being enacted in response to the climate problem. So just a couple examples of where we see these three different, if you want to call them themes related to justice, come up in climate. So heat waves is a big one where we have unequal exposure. So the distribution of heat across urban communities is one that you often will hear a lot about, because in urban communities that are richer, right, that have a lot of economic wealth, they are able to engage in greening. But in a lot of other communities, they don't have access to the resources needed to green. And so the albedo gets, right, really intense there because you have a lot of like dark surfaces. And so they're actually exposed to a lot more heat stress than other communities as a result of not having the infrastructure needed. And this is especially true of low income, elderly, and then Black, Indigenous, and people of color communities, especially in North America and the United States. Impacts of drought and desertification, unequal exposure to the harms or the risks that come about with drought and desertification to women, especially in the global south, because these are a lot of the individuals that are responsible for, right, securing food and water. And so they're having to go out of their communities in order to do so. That exposes them, right, to drought, desertification, intense heat, and desertification and drought actually make, right, that quest outside of their communities to get water and food or water for agriculture more difficult, right? Because they're having to travel further, go to new areas, because the ones that they were reliant on prior to climate change have disappeared. And then another one is sea level rise, right? So disproportionate impacts, especially low-lying, small, and large island nations. One of the examples that I'll give is looking at how that could happen in terms of West Antarctic ice sheet contribution to disproportionate sea level rise for low-lying island nations in South Pacific. So unequal burden, just to go through a couple of these, water and food scarcity will increase, right? This is especially going to be driven by considerations of extreme weather, as well as desertification, increase in drought, increase in heat. You have a lot with agricultural death. You're going to have agricultural death in places where they can't afford to irrigate or they don't have the infrastructure to do so. And so there's going to be a lot of communities that aren't responsible, again, because they don't have the infrastructure to utilize fossil fuels, right? Who are already experiencing social and economic injustices. It's going to be compounded by climate injustices, especially from extreme weather. And these are the communities that are not responsible for climate change. Energy transition disruption. So we already have, right, a pretty established infrastructure for energy and could afford to transition to green energy. But that's because we already have what we have because of our reliance on fossil fuels, right? Speaking from, an American perspective. But a lot of other countries have not been able to build up, right, their energy infrastructure relying on fossil fuels, and so can't make the transition in an economically feasible way towards green energy. But a lot of the nationally determined contributions and different types of thresholds that we're putting on fossil fuel use impact their ability to, right, engage in that kind of middle step, relying on what we might want to call dirty energy to get to the point where they have enough that they can make a green energy transition. So there's going to be disruptions, right, to those countries or those regions where they're trying to transition to having a solid energy infrastructure. Or it's just not going to be allowed based on some of the agreements that we've had. And climate migration, this is a big one. So recent reports have said that by 2050, it's estimated that climate migration from Latin America, Sub-Saharan Africa, and Southeast Asia will grow to 143 million being displaced by climate impacts. And so we think about extremes, we think about, right, desertification, water scarcity, food scarcity, just you're living on a coastline and you're constantly having to deal, right, with loss of life, loss of infrastructure due to tropical cyclone activity, right, increasing in frequency and magnitude. But there's also forcible dislocation, which we have from sea level rise, where people just actually won't have the lands that are theirs anymore because they will disappear due to sea level rise for a lot of those low-lying island nations. Last one I want to talk about quickly is unequal distribution. So reliance on fossil fuels tends to be higher in those communities, again, that haven't had the money or the wealth to transition to green infrastructure, right? And so if we're taxing, right, emissions, carbon taxes, you'll see a lot of people say that this is an unjust thing because those trickle down to the communities that are relying on and can't not rely on, right, fossil fuels at this point in time. And so the ways that we try to curb reliance on emissions for the wealthy have a tendency to trickle down to those communities that are disadvantaged and don't have opportunity, right, to rely on anything else. Coal mine reclamation policies are actually really terrible. If you look at what's being done with coal reclamation, at least up until about probably 2 years ago, in the United States, there's a lot of legal loopholes that allow you to just abandon your mine as opposed to having to deal with the regulations that are being placed on coal mines. And that essentially means that the entire community that is reliant on coal, right, for its local income suddenly just becomes unemployed, right? And it also leaves an incredible environmental hazard in terms of health hazard, right, for those communities. And again, this is compounding, right, already existing injustices because a lot of these communities where coal plants are socially, economically, and environmentally disadvantaged to begin with. EV subsidies, right? You're saying, oh, if you buy an EV, we'll give you a tax cut. Well, who can afford an EV? It's rich people. Do they need tax cuts? Probably not, right? So you're not getting an advantage in terms of, right, mitigating or the mitigation policies towards the people that might actually need the benefits in order to, right, move towards mitigating in the way that communities need to. And then this one is especially interesting. So this was an adaptation decision. If you look up the Great Wall of Lagos, there's a lot of information on what happened here. But they decided they needed to build a seawall to protect communities against inundation. But what they did is because you got to protect the rich people, they built the wall around the high income portion of Lagos. And then the water that needed to be like filtered off, right, from the inundation, because they built the seawall, they actually put it into the low-income communities, exacerbating flooding in those communities by relieving flooding in the rich ones. And then, in case you're not convinced that things are unjust, national insurance rates, right, are based on risk. And high-risk areas tend to be those where you have a lot of low income, and so you have insurance increase, right, because you're high risk, but they can't afford that increase. And then there's also, in addition to this, leveraging that can happen in high income communities, right, with insurance companies that can't happen because of political pull non-existent in those communities that are already experiencing unjust situations. Okay, well, what about the science, right? So this is all the impacts, this is the consequences of climate change. What does this matter for the science? Well, the science, right, can either contribute to helping us respond to these injustices, or it can exacerbate those injustices based on what we decide to research, how we decide to research it, whose voices and interests and perspectives we include in the way that we're doing the science, right? Questions we're asking. So an example of a distributive injustice in science is that the distribution of funding for research and access to supercomputing facilities, if we're thinking about, right, running something like CESM, 3.8%, right, of those types of climate modeling efforts that are funded are focused on Africa, okay? But here's the crazy part. Of that 3.8% of global modeling efforts or modeling efforts that are focused on understanding climate impacts, right, or climate change in Africa, 78% of that 3.8% goes to the global north. So the global north is setting the scientific agenda, determining what the interests of these African countries are, right? And they're only getting 3.8%, right, of the total, right, global scientific funding, and most of that is going to global north as opposed to the countries, right, that they're actually being studied. Some other things, right, procedural injustice. We make decisions on metrics and the significance of targets, like the 1.5 degree target for a climate-safe future, right, based on certain perspectives, certain values, which discount others. We make decisions on priorities and experimental designs, right, the SSPs, and the development of the socioeconomic pathways is an example of where you have certain value biases come in. It's very much representative of global north ideas about what various sorts of targets ought to be and what development trajectories can possibly look like. And then there's actually just what we call knowledge injustice. There's been systematic exclusion and marginalization in the development of our body of knowledge about climate change that's considered to be representative, right, of the objective body of knowledge, right? We have a lot of what's being done in climate science, especially if we look at climate modeling and we look at various endeavors like CMIP, very global north focused. We don't have a lot of voices, a lot of interests, a lot of consideration on what the experimental design looks like, what the models ought to be developed for, and how they ought to be applied by global south countries. And so we're treating this as kind of our objective body of knowledge, yet the interests that could drive research priorities, right, and research questions about climate change from the global south have been systematically excluded from a lot of these discussions. And that's actually one of the things that in the context of the Climate Justice Task Force and CESM that I'm a part of, we're trying to do better at here with respect to development and application of CESM. And I'll have information about that at the end. I'm going to go through these really quick. The papers are referenced at the end, but these are some examples of the way in which if we have concerns for justice, we can do science that's consistent with those concerns. So I'm going to give 3 examples. One is in investigating the implications of these targets that we've set for mitigation or adaptation endeavors. Another one is we define boundaries, thresholds of what's acceptable in terms of development or acceptable in terms of mitigation or adaptation versus what's not, right? We can make sure kind of that those thresholds and those metrics and those targets are representative of more than just, for example, what might harm people that are high income or part of the global north. And then actually recently, detection and attribution studies can be used to quantify loss and damage, which is something that hopefully COP will get moving so that those vulnerable countries that are least responsible for the climate impacts that we're experiencing, but are the ones that are getting the brunt, right, of the consequences of climate change can be given funds so that they can restore and repair after they experience damage and harm from these climate impacts. Okay, so the first one's really interesting. This study wanted to show that because of kind of the long time feedback for sea level rise in relation to Antarctic ice sheet decline and melt, they wanted to show that 1.5 actually is not a climate-safe trajectory for a lot of nations, because even with 1.5, that long-term feedback will result in sea level rise that will displace a lot of populations in the low-lying island nations in the global south. So what they did is they actually used CESM, and they did a study where they ran a couple of ensembles, and they looked at what would the contribution from the West Antarctic ice sheet to sea level rise be. But then they wanted to look at, is that disproportionate to certain locations, right, that are subject to potential risk of sea level rise than others, and did what was known as this fingerprint study, and demonstrated that even under slowed warming projections, you will get uneven distribution of sea level rise, which results in, right, complete displacement for some of the small, low-lying island nations in the South Pacific, even under what we consider, right, a low, right, trajectory where we mitigate a lot and we try and reach a temperature target. And so they basically conclude from this study that, right, our obsession with global mean temperature as the target we're trying to hit with mitigation is not consistent with the goal of avoiding dangerous anthropogenic interference in the system, because even with that temperature target, we can have certain consequences that go unnoticed, right, because these voices are not represented in the room when we're talking about 1.5 being our target. Another example is with constraining the Earth system boundaries. So here, basically what they did is they said, look, we're going to think about what is an acceptable threshold for just and safe, right, living for human and non-human actors for various sorts of, right, categories of the Earth system. So they thought about the hydrosphere, the atmosphere, right, the nitrogen cycle, various other cycles. And they looked at whether or not 1.5 and various other sorts of temperature targets that we're thinking about would keep us within the safe and just bounds, right, for having global water security, right, for having justice with respect to allocation of water and what's happening in the hydrological cycle. And unfortunately, they found that if we look at the climate, biosphere, water, nutrient cycles, aerosol pollution, additional pollutants, and we use an ESM to do this, we see that significant harm is indicated not even at 1.5, but at 1 degree. So we've already passed the just and safe Earth system boundaries for a lot of components of the system. And Cecile is going to kick me off in a second, but this one's really interesting. So what they did is they looked at performing attribution studies for Hurricane Harvey. And they did a basic attribution study saying, okay, what was the increase in damage or increase in consequences and impacts from Hurricane Harvey that could be attributable to anthropogenic climate change? They found that there was a certain amount of increase in magnitude, right, and duration, especially precipitation due to anthropogenic climate change. But then the interesting thing is they coupled this with an economic study to determine, one, how much additional money was spent, right, in response to those impacts that came from the increased magnitude and the increased duration. And they found that it's somewhere up here, I think it was like 13 billion. Is that what it says up there? Yeah, 13 billion. Too much text on the slide, sorry. But they found that it was $13 billion. And the more interesting thing that they did is they wanted to understand how this was disproportionate to certain neighborhoods and communities, and whether or not those disproportionate impacts were those especially vulnerable communities that got a lot of the damage and required a lot more in terms of economic response and loss. Okay, so what about modeling? Well, this is what I have to say. The decisions we make about how we develop the model, how we use the model, development, configuration, experimental design, our application, the metrics we use to determine model skill, and even communicate outcomes or outputs of the model to people that might be using it for adaptation or various other sorts of applications can be consistent or inconsistent with things like concerns for distributive justice, procedural justice, etc. And so we can do something about that as modelers. And so one of the things that we can do is we can increase transparency around how we're making decisions. Why are we picking 1.5? right? Why are we representing irrigation in the way that we're representing it? Is it based on an understanding of what irrigation looks like in the global north that doesn't capture irrigation practices in the global south, which might, right, make our model inadequate for the purposes of simulating certain agricultural changes in the global south? We can also have greater inclusivity and access, diversification of our instruments, right? Regional models that are fit for purpose for different regions would be a great thing to have and could be run on simpler, not so high-tech computing systems. Prioritized applications, right? All these things could increase justice in terms of knowledge justice in the context of climate change. And if you're interested in that, shout at me or whatever that like thing is at me or something. I don't know, whatever. I'm embarrassing myself at this point. Use that QR code and you can sign up to be a part of the Climate Justice Task Force. And if you have any questions you want in the literature, that is my email. Thank you.
Thank you so much. We have 4 minutes for question because we have to lock with Rory at 2:45. Then yeah, but I will ask you to stick after the break.
Sure.
That yeah.
Thanks, Monica, for the lovely presentation. My question is, I know with all you've said now is mostly there are challenges, but is there any way that this climate justice thing is being looked at in the design of protocols now with regards to CMIP 7? Now I know the other CMIPs are gone now. Are there any effort being made that the protocols for CMIP 7 incorporate some of these things so that you can see the outcome?
Yes. So there are initiatives, and I'm actually part of one, to try to get ethics into the way that we're conducting CMIP, what we're doing, how we're making choices about variables, what it means if we're fast-tracking evaluations of model capability, how we share the data, how people access the data. I would love to talk with you about that. So just send me an email because we're looking to bring in individuals, right? Because we don't really have a lot of people from countries that might not have access to data, might need different access protocols, things like that, to understand what that might look like. So yeah, it'd be helpful to have your voice in the room.
Hi, thanks. That was such a great talk.
Thank you.
One thing I'm really interested in is how you, like, for example, the small low-lying island nations that are already projected to be inundated, how do you have a just response to an unjust thing that has already happened or projected to happen? Like, how do you solve it? Or more like climate adaptation versus mitigation?
Yeah, that's an excellent question. So quick answer would be we get the countries that are responsible, right, to provide resources so that those countries that are going to experience, right, a lot of these incredible harms as a result of climate change can adapt. Interestingly enough, there is, and I can't remember where it is in the South Pacific, but they actually have developed an adaptation strategy, right, where they can kind of move the island a little bit by putting up various barriers, which like brings in sediment from the waves. So like it moves the island a little bit, but they're thinking that it might actually prevent complete inundation from sea level rise, so that like country and that land and that culture doesn't disappear. I'm happy to find the resource. The thing is that you need money to be able to do that, right? Especially across all the low-lying island nations where that adaptation effort might be applicable. And so, right, getting United States of America, European countries to pay their fair share is really what we need to do. And I know COP has been working towards a loss and damage fund. So we'll see come November what progress is made there.
Okay. Yeah, 1 minute because we have. Yeah, can this one? Yeah, because we have Rory at 2:45. Then.
Okay. Oh, there was? Sorry. You can email me. I'm always happy to talk. I love talking.
I'm super interested. You were bringing up like
changes to models and thinking about things like attribution studies. And one of the things I'm curious about is scientifically a lot of that is so hard still right now. Like doing a good attribution study for a lot of things is just like out of reach, or not out of reach, but like not able to be done very accurately right now. And so I'm curious if you are trying to also like drive directions of scientific development and how you go about that and inform that type of direction.
Yeah. So, and I mean, on my last slide, the attribution study slide, I think the last point, and you guys can look at this online, was something about how like 78% of the funds that are being allocated to attribution studies are to look at the loss and damages in the global north, right, as opposed to focusing on, right, loss and damage in those like countries where they would need to adapt or they would need funds, right, in order to restore and repair. I think that we do have, I hope I don't get in trouble for saying this. I think that we do need to kind of reorient ourselves towards different sorts of questions in climate science. And I do, to some extent, see that happening. What I don't see happening and really worries me, and I'm surely going to get in trouble for this one, is that with respect to our modeling agendas, we have a tendency to think that, for example, uber high-resolution global models are going to provide us with all the information we need in order to respond to climate change. And so we're not balancing our resources and our development of resources in the way that we need to actually answer all the questions that need to be answered for the science to become just. So we kind of need to do that better. And it could start with something like CMIP. It can start with something like CSM. But yeah, I guess we just have to keep pushing that, look, there's a lot of different questions that we need to answer to, and there's different tools that are suitable for answering those different questions. And so let's not put all our eggs in one basket.
Okay.
You can talk to me afterwards.
Yeah,
you know where to find me, Timmy Joe.
Yeah, let's talk. Yeah, let's keep, because we have to do a big experiment now to make sure things are working for tomorrow. Then I'm going to contact Rory here. Oops. Sorry, I'm just doing this to see if it's there. Oops. Hey, Rory. And yeah, this is Rory that's here. And he's going to help us to go. You all know Rory, then you can say hey. But it's because we are going to. Can you follow the slide on the YouTube channel? If wait, I cannot hear you. Wait, oops. Okay. It's okay. Can you hear me? Oh. Yeah, I can hear you. Okay. Okay, then, yeah, let's go. Maybe we don't even need you. Maybe everything will work fine. Okay, then daily check-in. Then the first thing I want to remind everybody, the code of conduct, that's very important to us, with all the link that you can explore here. But now, last year, when we did the last day, it was not the last day last year, but when we did the diagnostic, we had to log to the Jupyter Hub, and we had 80 people who log at the same time on the Jupyter Hub. And then the Jupyter Hub saw it was an hacking attack, and they closed down. And then we could not do our lab that day, and then anybody could not work anymore, then it was kind of tricky. Then CESL has been working on a solution for this doesn't happen, and it's why Rory is here helping us. He has done a lot of effort, but we want you to test. Then please bring your computer. We are going to try to see if when we all log together, if the Jupyter Hub is going to survive. Then can you go to this link? Everybody, and we are going to go through this together. So far, so good.
The most helpful if everybody logs in like all at once.
Sorry?
I just said it will be the most helpful if everybody logs in all at the same time.
Yeah, then we are going to do it at the same time. Then don't log yet, you go to the link and you don't log. You just go to Jupyter Hub, you bring this window, but you don't push on the submit button yet, okay? Then everybody goes to jupyterhub.hpc.ucar.edu. And when you are there, you put your username, you can put your password, but you don't push on signing yet. Because we want to see if the machine can handle this. Not yet, yeah. Don't push on signing yet. Yeah, we will do, yeah. But first bring this window and yeah, don't do any duo now. Bring this window. And don't push signing. Who is not there yet? Okay, we wait, yeah. Yeah, I had this problem too. Each time I lose the internet, and then it takes a long time to come up. Then, yeah. Okay, are you there? Yeah, Temilop, yeah. Sorry? Oh, yeah, you should not be there. Okay, I don't know how you are there already. Then I have somebody that's already in the window, like if they log in before.
I didn't even give password username.
Okay.
I never saw this screen.
Yeah, then I have somebody that's on this window already. Yeah, but he said, yeah. Wait. Let him answer. We don't want, okay. He's on the window. Oh, okay, now it's good. Okay, it's good. Yeah, if you haven't clicked, you should not be there. It was something, yeah. Okay, perfect. Don't click on anything. Are you ready, Temilo? No. Okay, everybody is ready. Then you are going to put your username and, yeah, okay, that's okay. One person, it should be okay. Tomorrow, if it crashes, we know it's because of you. Ali, if it crashes tomorrow, it will be you. Then enter your username, password, and then when we say 1, 2, 3, you put on sign in, and you will have to do the duo password. Yeah?
I did not sign in and it comes here.
Oh,
and it did it.
yeah, do log out.
Okay, log out.
And then it will come back, even if you are just, yeah, it's okay. Okay. Are we ready? Are you ready? I think it's not that crucial that it's really simultaneous, but 1, 2, 3. I should have done it too. They are doing it now.
Okay. We'll watch. Let me know if they start successfully getting pushes and signing in.
Okay. Are you getting pushes on your phone? Yes, some, yes. No. Some are getting pushes, but not everybody.
Okay, and then so some might not be getting pushes, maybe just because the library the main seminar Wi-Fi is busy. Also, maybe they have bad cell service.
Yeah.
But now the ones that have gotten signed in, see if they can start sessions.
Okay, then, yeah. Okay, I'm going to go to the next slide. If you are not having a pushes, we will come, but he wants to see. Do you see this now?
No, not yet. It's just rotating.
Oh, it's just rotating, something rotating.
So they push the button and it's not signing them in yet?
Yeah, it's rotating.
Can you, by show of hands, guess how many have gotten in? Like you ask them.
Does somebody okay, who is on this thing? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 15 are on the thing so far.
Okay.
And the number is increasing. And don't feel bad if you are not on it, because it's not your fault, it's your fault. Okay, they're on it. Okay, it seems they are all getting on it. Okay, this is good. If you are not on it, don't worry. We will figure out later. Yeah, just we want to, because I think if the majority gets on it for now, it's fine, and tomorrow we can get everybody. Is it okay like this, Rory?
Yes.
Okay.
Yeah.
Okay, then don't push on anything there. You go now. It should show you something. If you go to push now on the, let me go back to the button, start. Then if you are here, you do start server. You push on the little button there, start, and then it should bring something like this. You don't do launch server. You wait there. We have to change this from Casper login to Casper PBS batch. But yeah, click on start here, and it should bring you something like this. But don't push on launch server yet. We are hopeful. We are very excited. Are you? Okay, are you? Yeah, it's fine. Then if you are there, then you can change Casper login. If you change here in the little window at the top, Casper login, you change it to Casper PBS batch, and it will show something like this. Okay? Then, when you are there, the first one, it's a Casper PBS batch. The second one, we were hoping that you have access to tutorial, but we have been testing frantically in the last hour, and it doesn't work yet. But you should have access to something that's called R190302. Then you select this one, and you select the project UE. Yeah. Yeah, the tutorial shows up, but when we were doing it, it will crash. Then they have the, yeah, I had the tutorial showing up. I did it many times. I have been in contact with Rory, and the tutorial will show up, but when I will try to launch the server, it will crash. It will tell me that it doesn't recognize this account. Then for now, do it this way, and tomorrow we will do it. You will have fixed it for tutorial by tomorrow, you believe?
The tutorial, yeah. If not, I'll tell them the numbers to type in tomorrow, but we're hoping to be tutorial.
Yeah, tomorrow we hope it's tutorial, but today don't do tutorial, it will not work. Then do the other number, and then you push on, when you have this, you push on the button launch server. Okay? We don't have to do 1, 2, 3, you can push when you are ready. And then you should arrive with something that looks, this is my own window, then there are a lot of stuff, but you have something that looks more or less like this, without everything on the right side. Okay, then the top, Casper PBS, this number, and this. Okay, let me show. Let me see. Oh, okay. Yeah, you cannot use the tutorial. Don't use the tutorial queue. You should use this number. You should not use the tutorial queue. It crashed. It's not working. Let's do this. Launch server. Oops. Okay, can you push on? Yeah. Don't use the tutorial queue. It doesn't work yet. But this is. Does it work for anyone? Waiting. They are waiting still, but. Who have something that looks like this? Okay, we have 2 people that were able so far, 3. When you have something that looks like this, raise your hand. 4, 5, 6. It's going slowly, but is it fine? You will not have this on the side. This is my stuff, but you will have the rest. Blue fire. Wow. Is it okay? Okay, who doesn't have something like this yet? Oh, okay, then wow, yeah, then we have probably 10% that were able to arrive there yet. It's doing something, but show me what it does. Yeah. Yeah, then I'm going to show him. This is what they get, then it does something, but it does this.
That's not very exciting. Let me look at the reservation.
Okay, he's looking at, but some people went in, yeah. Thanks for your patience, but it's... No, it's the server that cannot handle so many. Okay, any more luck? Who cannot connect? Oh, okay. Somebody got an error. Can I see the error? Who has an error? Okay. Yeah.
So I've gotten that. I don't know.
Okay. Let's show him, yeah, then. Yeah. Yeah, then she has an error here. Error loading team still. Oh, this. I'm going to send him a picture because sorry. Oh, but maybe it's coming.
It's error and then and then it is.
I also got an error.
Did you get
Did
this?
you get? No, I got
You will be ready. Yeah. Yeah, no, we are getting some error.
Okay, and see where.
Yeah. Okay, we are getting some error and. Yeah, can you show the error? Then Michaela here, she gets this.
I got that one too.
And several people get this.
Yeah, mine says that
Okay, it's possible that they're maybe just that one. Can you give me the username?
What's your username?
Fendrog, my last name.
Yeah, go. Yeah, this is
It's Fendrog, my last name.
Fendrock. FENDROCK.
Okay. Does she know her username?
Yeah, this is the last name. It's FEN. Yeah.
Okay, hold on.
And I have another one here. Yeah, it's about to sex. Oh, you got the error. Oh yeah, then people. Okay, then it takes longer time. But if it takes a little bit, 5 minutes, it's okay. But last year we never succeed to get in. It was never. Then they've been working very hard on this. Do you see anything? Or?
Still looking. So Fendrock is not in the reservation, so that explains that.
Oh, you are not in the reservation. Okay.
I'm sure that's the same for me.
Okay, and maybe Bartusek. As Bartusek is maybe it's not in the reservation either. Okay, do you think you have enough information for now, Rory? Okay, then now we are going to quit. I make them quit this, okay? Yeah, then, okay, I think the test is good enough. Then if you succeed to log in, do log out now. It's just that we have information to see if something is at least happening.
So just close out of it?
Yeah, you can do log out. You go to the top file and you do log out. I think it will kick you out automatically after 2 hours, but okay. Okay, then, yeah, is it enough information?
Yeah, I mean, for sure from our side, much better than last year.
Okay, it's much better than last year.
We can tune tonight. We have a knob we can tune tonight to maybe make it even a little better tomorrow.
Okay, thank you so much. Yeah, thank you, Rory. Okay, bye. Bye. Okay, they're hopeful, then it's much, much, much better than last year, but it's not difficult because last year it was not working at all. Then they're hopeful they can even make it better. Thank you for your patience and your test on this. We are going to move to the lab to continue to work on the lab session that we are working. Yeah, any question? Or don't worry if you were not in, we will get you tomorrow in it. But